When Galileo discovered Europa in 1610, along with three other moons of Jupiter, his telescope showed them as only star-like points of light. But even that low resolution was enough to show that the moons orbited Jupiter and prove that the Earth is not the center of everything. Europa is about the same size as our moon, but is typically a couple thousand times farther away. So over the following centuries, viewed from telescopes trapped on Earth, Europa remained only a single unresolved light point. Even so, important information came from that point of light. Europa's wavelength spectrum, what our eyes crudely see as color, depends on the material on its surface. Instruments developed during the mid-20th century could accurately measure such spectra. Using a spectrograph and including measurements at infrared wavelengths, too long for the human eye to see, 1972 MIT graduate student Carl Pilcher correctly inferred that Europa's surface is predominantly water ice. With the Voyager and Galileo spacecraft, we could carry cameras close enough to resolve Europa's surface in detail. These cameras had a resolution of 800 by 800 pixels, considered low by today's digital camera standards, but compared with the single-pixel views of Europa from Earth-bound telescopes, they were revolutionary. And we could get some great close-ups. These cameras had telephoto lenses, and occasionally, the Galileo spacecraft swooped just over the surface. So, the complete photo record includes broad global-scale coverage, more detailed coverage of about 10% of the surface, and a few telling close-ups. The images are spectacular, but the revelations of what lies below Europa's sunlit surface are even more exciting. For starters, subtle variations in the spacecraft trajectories caused by Europa's gravity constrain the Moon's internal densities. There is a metallic core with a radius of 700 kilometers, a rocky mantle, and an outer layer approximately 150 kilometers thick, with liquid or solid water density. Europa's water had to be frozen at the surface because, without a blanketing atmosphere, any heat radiated rapidly into space before it could melt the ice. However, below the surface, much of the H2O layer is probably liquid, according to estimates of internal tidal heating. With such a thick layer of liquid water, this moon-sized body has a global ocean comparable in volume to the combined oceans of the much larger Earth. The presence of large amounts of water surrounding a rocky interior had been predicted in the early 1970s by Guy Consolmagno, another MIT student, and John Lewis, his master's thesis advisor, based on theoretical models of how the satellites formed. According to these models, Jupiter's moons formed from a huge swirling cloud of dust and gas surrounding the young planet, just as the planets grew in a similar cloud around the Sun. As this Jovian nebula cooled, solid particles condensed out like snow forming in a cloud on Earth. The particles gradually accreted together to form satellites. The sequence of condensation determined the composition of each of the satellites. The internal heating separated the materials by density within each satellite, with dense metals sinking to form a core and lighter stuff rising toward the surface. A thick layer of H2O on Europa was expected long before Voyager or Galileo arrived. As soon as the possibility of an ocean was raised, speculation about life began. Guy Consolmagno believes he first raised the issue in his master's thesis, despite controversy about who suggested it first. He is now a Jesuit brother working at the Vatican Observatory, so he is reasonably credible. Additionally, based on my personal knowledge of Guy, I would trust him regardless. What is it like down in that giant ocean under the ice? We know nothing about Europa's ocean floor, but a surprising amount of research has been based on speculation. Undersea volcanism has been discussed in detail because when the ocean was believed to be isolated below the ice crust, volcanoes seemed to be the only source of heat and chemicals that might offer hope for life on Europa. The volcanic models were not motivated by any observations of Europa, but rather by recent discoveries of life supported by undersea volcanic vents on Earth, and by the dramatic volcanoes on Europa's sibling Io. Europa has no observational evidence for or against volcanism or anything else under the ocean. We do, though, have plenty of observations of the surface. What we see in those images is key to understanding whether the ocean has what it takes to support life. The possibility of life no longer depends on speculation about undersea volcanism. We have excellent images of the surface of the ice because cameras on the Voyager and Galileo spacecraft had sensitivities and wavelength ranges that vastly exceeded those of the human eye. Even low-resolution global views, worse than 10 kilometers per pixel, reveal much more than the uniform white water ice that would be visible to a human observer, as shown in color plate 1. At this resolution, dark orange-brown markings of still unidentified substances on the bright background come in two major categories. Splotches ranging from tens to hundreds of kilometers across, and a network of narrow lines. The lines and splotches provide a first indication of what will prove, based on higher resolution and considerable analysis, to be the two major resurfacing processes on Europa. Tectonics, the lines which basically indicate cracking, and formation of chaotic terrain, the splotches, which are essentially the result of melting. As we shall see, each likely involves direct ocean interaction with the surface by cracking or melting. As Europa orbits around Jupiter, it keeps one face toward it. To achieve that, like the Earth's moon, it spins on its axis with a period that matches its orbital period. We refer to this behavior as synchronous rotation. Actually, while the moon's rotation is exactly synchronous, Europa's is nearly synchronous, but close enough for now. Later in this film, I discuss evidence that Europa's rotation is non-synchronous over the longer term, and that the whole surface slips around relative to the poles. However, at least during this period of human observations, the Jupiter-facing hemisphere has been nearly constant. Synchronous rotation helps us define a latitude and longitude system, which we must use to discuss locations on Europa. Latitude is easy to define. Just as on Earth, we measure it relative to the spin poles and equator. But how do we define longitude? On Earth, we define the prime meridian, 0 longitude, as running through the Royal Observatory in Greenwich, England. On Europa, also by convention, the prime meridian runs through the point closest to Jupiter, which, for practical purposes, is fixed on the surface, thanks to the synchronous rotation. A major landmark in the trailing hemisphere is the X of Europa, formed by two globe-encircling dark lines that slightly cross at a right angle to the edge of the disk's center. This neighborhood is critical for several reasons. This neighborhood well represents the two major types of geologic processes. The intersecting lines that form the X are global-scale tectonic features, and the dark patch in the lower crotch of the X is Connemara chaos, the archetype of what has come to be known as chaotic terrain. Most importantly, we have unusually complete photo coverage there. The detailed images of this area have given us great insight into the character and dynamics of Europa's active surface. At the same time, over-reliance on this site has produced some widely promoted generalizations about Europa that were not well justified, causing considerable confusion and misunderstandings. With appropriate attention to such pitfalls, the images of the Connemara area provide the key to what is seen across Europe. The X at Connemara is also a convenient landmark for locating other images. The X lies just north of the equator and very close to the center of the trailing hemisphere at 270 degrees. In addition to Connemara, other geographical points of reference are important later in the story. We refer to the dark bands south of the equator as the wedges, due to their tapering shapes. The markings divide the surface into distinctive rounded boxy shapes, evident even in these low-resolution global views. Toward the north lie several long, dark, roughly east-west lines. which cross one another at oblique angles. Eudaeus and Minos linea. The Eudaeus-Minos region is important for several reasons. It has typical examples of large worldwide lines. The tectonic features here are key to understanding Europa's rotation. And similar to the X at Connemara, these markings help us find important sets of clearer images. Tectonics, chaos, and lines dominate Europa's global scale. Equally important as the ubiquitous splotches and lines is what is missing: craters. Unlike our moon, unlike the other icy moons of Jupiter, and indeed unlike most bodies in our solar system, Europa has hardly any craters. Bombardment by small bodies has had a minimal role in shaping the surface we see today. Only a couple of impact features are evident at this scale. Crater Puil is about 1,000 kilometers due south of Connemara, appearing as the dark spot about 20 kilometers wide in global views. That Puil is an impact feature is evident from the enormous system of bright rays of ejected ice that extend 1,000 kilometers or more in every direction. One ray even crosses the western side of Connemara chaos. As a result of this whitening of its western side, Connemara, which is diamond-shaped, appears to be more triangular in the global view. Another prominent impact structure is the Callanish dark circle near the eastern edge, just south of the equator. This large feature, about 60 kilometers across, differs from the splotches of chaotic terrain viewed at this scale. Its round shape hints at its impact origin at this scale. Higher resolution images confirm its impact origin, but they also suggest some intriguing similarities to chaotic terrain. Both may represent breakthroughs for the liquid ocean. Why are there so few craters? The answer is likely similar to Earth's. Active geological resurfacing on the planet has erased nearly all impact records. The current surface must be less than 50 million years old, or it would show far more craters than it does. We know of no major event that wiped the entire surface clean all at once about 50 million years ago. Instead, the continual, gradual resurfacing manifested by chaotic terrain and tectonics provides a ready explanation for Europa's youthful appearance. In summary, these three low-resolution global views effectively introduce the main points of our story. Features representing the rapid and ongoing effects of resurfacing dominate Europa's appearance. The global view shows the two major categories of the resurfacing processes: tectonics and chaos formation. As I show later, these processes not only modify the surface, but they generally provide, in diverse ways, access between the surface and the liquid ocean. The dark material that marks the sites of these processes is indistinguishable from one site to another. It looks the same where it marks linear tectonic features or chaotic terrain. This similarity reflects a common feature of these processes. They all involve the interaction of the surface of the ice with the ocean. The dark markings may represent the concentration of impurities as the ice was warmed by nearby liquid water, or they might consist of recently exposed substances from the ocean that lie just below the ice. The implication seems inescapable. The surface features of Europa suggest a dynamic, ongoing connection between what lies above and below. Global images were a revelation, but the best was to come as Galileo made closer passages to the surface and the images zoomed in with increasing detail. Color imagery shows a 1,000-kilometer-wide portion of the Eudaeus-Minos region, a relative close-up compared with the global views. Many scratchy dark lines resolve into double lines, typically about 10 kilometers wide, with a bright lane between them. Planetary geologists have given these double lines the name triple bands. They counted the central lane between the dark lines, but the central lanes were not brighter than the surrounding surface. Another quirk of this terminology is that, in Europa, the term band is generally used to describe dilated cracks, where adjacent plates have pulled apart. As we shall see, the only thing that triple and dilational bands have in common is that both are initiated as tectonic cracks. We also see many dark spots at this scale, typically about 10 kilometers wide and quite common in Europa. During the early part of the Galileo mission, the International Astronomical Union, the organization charged with naming things in space, deliberated at length about what, or even whether, to name this feature class. My doctoral student Randy Tufts called them freckles, but astutely recognizing the cachet of Latin in academic circles, he proposed the term lenticular, which means the same thing. The spots got their official name. As we shall see, most of these spots represent minimal patches of chaotic terrain. Many appear to be about 10 kilometers wide because such patches usually have a dark, several kilometer wide halo around them. That typical halo size is independent of the size of the chaos patch. So, no matter how small a patch of chaos may be, it may appear to be about 10 kilometers wide at this resolution. This effect explains why so many spots are about 10 kilometers wide, even though the chaotic terrain has no preferential size. There has been a lot of confusion caused by the misuse of the term lenticular. The key is that it was defined to describe these dark spots as they appear on low-resolution images, where brightness variations could be seen but not surface relief or morphology. The similar but larger splotches also prove at higher resolution to be chaotic terrain. The practice of assigning different names to a single type of terrain based on its imaging resolution has caused astounding confusion. Low-resolution observations of those larger splotches, beginning with Voyager, led to the term mottled terrain. We introduced mottled terrain, similar to lenticular, to describe darkened patches on the surface. So a patch of mottled terrain Atubblad, Tauseptan Trasham, is the same as a lenticular, only bigger. However, at higher resolutions where surface relief is visible, mottled terrain, similar to most lenticular features, aligns with chaotic terrain. I use the term chaotic terrain in this film because it is based on better and more complete imagery than when mottled terrain was invented to describe low-resolution pictures. Another zoom-in from the global scale shows the broad area ranging from the Big X at Connemara all the way south to the impact crater Pwill, about 1,000 kilometers away. Compare this image with the global view. Once again, the higher resolution reveals the division of global scale lines, such as the X's, into two dark lines. We can see more clearly the ray pattern of material splashed out from the impact at Pwill. Connemara Chaos, nestled into the crotch of the X, is diamond-shaped, 80 kilometers across, with a wisp of bright ejecta crossing its western side. Despite being better than global views, the kilometer resolution images are still annoying. We can't tell what it is we are seeing. Part of the problem is that to enhance information about the surface material's reflectivity and colors, those images were generally taken with direct sunlight illuminating the surface from nearly perpendicular to the surface. But that illumination hides the surface's morphology, relief or shape. There are no shadows, slope-induced brightness variations, and few surface structure clues. We cannot see any hills, ridges, pits, valleys, gorges, cliffs, or other landforms that might appear on a planetary surface. In the images above, we have seen markings corresponding to the important geological features and processes, but there is no direct evidence yet. Part of the explanation is that Europa does not have much topography. Hardly any features vary by more than a couple hundred meters from the mean elevation, and slopes are gradual. Europa is one of the smoothest bodies in the solar system. But to understand the geology, we need to look at higher resolution images with sun angles low enough to reveal the bas relief of the subtle surface structure. Galileo imagery includes coverage of about 10% of the surface at a resolution of 200 meters per pixel. We would have had much more coverage if not for the failure of the spacecraft's high-gain communications antenna. However, we planned these images with a geological survey in mind, so the illumination generally reveals the surface's shape well. In fact, the high quality of these images does exacerbate our frustration that they cover such a small fraction of the surface. On the other hand, the images we have, combined with the broader context seen at lower resolution, suggest that we have sampled most of the major terrains, structures, and processes. The more oblique lighting shows the Connemara area at this higher resolution. With this illumination, the topography is evident. The brain can produce optical illusions when viewing an unfamiliar object. Sometimes hills can look like holes, or ridges appear as troughs. Chaotic terrain in Europe proves to be the site of disruption, where blocks of the older surface have been separated and displaced, like rafts of ice within a melted patch of lake ice on Earth. The bright ray of ejecta is still apparent, running north-south across the western side of Connemara. The structural details of the lenticular are visible. 3 dark spots north and northeast of Connemara, and even visible in the global images, are resolved into small patches of chaos, each with a dark halo, a detail that was not evident at lower resolution. Where there is no chaos, the terrain is densely covered by mutually crisscrossing ridges ranging in width from about 1 kilometer wide down to as narrow as the image can resolve. Even this brief first look at Europa's surface touches on many of the issues of Europa's science, which are detailed. Most broadly, Europa is dominated by 2 classes of terrain: tectonic and chaotic, which correspond to the dominant effects of stress and heat operating on the icy crust. Some of the most dynamic resurfacing involves ridges forming along cracks and chaotic terrain. To complete this introduction to what we see on Europa, I focus on the appearance of ridges and then on chaotic terrain. The major ridge complexes that make up the global scale lineaments, like the Big X at Connemara, each consist of multiple pairs of parallel ridges. The pairs are roughly parallel, although they cross or intertwine in various places. The ridge complexes are bright, at least as bright as the surrounding terrain. Surprisingly, the darkening that characterized these global-scale lineaments is hardly evident here. Why did the triple bands disappear in this picture? If we look carefully, we see that along either side of the major ridge complexes, the adjacent terrain is slightly darker than average. This subtle, diffuse darkening is shown as the dark lines on the contrast-enhanced global-scale images, or as the double dark components of the triple bands we have seen at intermediate resolution. The faint double dark lines lie between the ridge systems, which now reveal themselves as the most significant structure of the global lines. In the lower resolution images, they appear as the relatively bright center line of the triple bands. The dark coloration on the margins of the ridge complexes, which seemed so prominent in the lower resolution images, is barely recognizable in higher resolution images with oblique illumination. These darkened margins themselves do not directly mark any topographic structure, except that the surface is smoother and lower where it is darkest. The significance of the darkening lies in the correlation of the coloring agents with ridge complexes. The ridges probably mark cracks along which ocean water has been able to reach the surface. Thus, these margins are the first of several examples of darkening and perhaps smoothing associated with oceanic exposure. Major ridge complexes consist of double ridges. In fact, nearly all ridges on Europa come in pairs of identical components, each pair remarkably uniform along its length. The terrain surrounding Connemara consists largely of crisscrossed double ridges. We can zoom in on an example with one of the rare, very high-resolution images. With Galileo's limited picture budget, only isolated sites have been observed so well, but they reveal the character of the types of terrain. We see typical densely ridged terrain. The previous surface has been covered repeatedly by newer ridges, each crossing what was there before, until nothing is visible but ridges on top of ridges. The largest ridge pair crossing this field of view is about 2 kilometers across and about 100 meters high, about as large as any ridge gets on Europa. Among the youngest features shown here are very fine cracks crossing and cutting older ridges. The double ridges may have formed along the borders of such cracks, while the recent cracks may not have had time for crests to form. This densely ridged terrain is sometimes called bright plains, or even worse, background plains, both misnomers based on low-resolution images. The areas looked smooth because the ridges were not visible. Even worse, the term background plains promoted a misleading implication, as used by the geological mappers of the Galileo imaging team, that it is the oldest type of terrain on Europa. That terminology also suggests that Europa's surface appears young because of a hypothetical slate cleaning event that created an initial state for subsequent geological processes. However, there is no evidence that resurfacing has ever been apart from a gradual process of continual renewal by a fairly constant set of processes. As higher resolution images showed the true character of this terrain, the earlier terminology became obsolete. We should have abandoned terms like bright plains and background plains, along with mottled terrain and lenticular. Unfortunately, their use has continued, resulting in a confusing taxonomy. Classifying a single terrain type in multiple ways is dangerous, depending on how it looks in different pictures. This practice has caused confusion, misunderstandings, and incorrect generalizations and inferences in Galileo's science analysis. The common denominator for all ridge systems on Europa is that ridges come in pairs. Contrary to a too common misconception, the double ridges do not correlate with the double dark lines of triple bands as seen at kilometer-scale resolution. That confusion may stem from an early montage from a Galileo press release, used in numerous review talks by Galileo spokespeople, that showed double ridges blown up to match the size of a triple band displayed next to it. I want to emphasize the correct relationship between ridge pairs and triple bands. Ridges are fairly bright, each about 1 kilometer wide. The dark margins present a distinct contrast. They are typically 10 kilometers wide, are found outside the area of the ridges, and are only associated with multi-ridge complexes, like those that constitute the X in Connemara, or with a few of the largest ridges. The double dark lines are only pale, diffuse markings, while the double ridges, as a class, represent one of the most important and telling morphological features on Europa. Ridges are important because they cover so much of the surface, but they also serve as a marker of one of the most fundamental geophysical processes at work on Europa, crust cracking. According to the following train of logic, ridges correlate with tensile cracking in the icy crust. The global and regional lineaments correlate reasonably well with theoretical tidal stress patterns. We assume that simple double ridges, which comprise complexes of these lineaments, are similarly associated with cracks. Moreover, double nature is due to ridges running along each side of a crack. Tracking the ridges on Europa gives us a way to unravel the history of cracking Europa's crust. The ridges' paths show the history of tidal stress. Some characteristic patterns even provide our first geological evidence that an ocean lies beneath the thin ice shell. Tracking these tidal stress patterns will be a big part of the story, but first, let's take a closer look at what tidal heat can do to the surface. Camara chaos is a typical chaotic terrain. We have already seen it in a sequence of ever higher resolution images. A set of high-resolution images spans a belt across the southern half of Connemara, showing much greater detail. Throughout Connemara, the surface appearance suggests thermal disruption, leaving a lumpy, bumpy matrix with somewhat displaced rafts on whose surface fragments of the previous surface are clearly visible. Chaotic terrain looks like a place where the crust briefly melted, allowing blocks of surface ice to float to slightly displaced locations before refreezing back into place. Similar features are common in seasonally frozen lakes or Arctic sea ice, where the underlying liquid has been exposed. The formation of chaotic terrain clearly represents the destruction of an earlier surface. In the case of Connemara, that earlier surface was tectonic terrain. The surfaces of the rafts still display fragments of terrain covered with ridges and cracks. Essentially the same terrain that immediately surrounds Connemara. The rafts, resembling picture puzzle pieces, easily reassemble into relatively continuous areas, typically reconstructing a few major ridge systems that traverse the region. However, the destroyed surface cannot be reconstructed, because most of it has been broken into lumps too small to show their earlier surface or too melted to retain their original shape. While the formation of chaotic terrain has destroyed the previous tectonic terrain by breaking it up and melting much of it, we can also see the revenge of tectonics. After Connemara formed and refroze, more cracking occurred. We can recognize cracks that formed after Connemara chaos because they cut through the lumpy matrix, and when they reach rafts, they either slice across them or wend their way among them. They differ from older tectonic features that only lie on the rafts and not in the matrix. One example of a post-Connemara crack runs diagonally across the lower left corner. Another crack snakes toward the upper right, making its way among rafts, along the northern edge of one of the larger rafts, and across the lumpy matrix. This example has already begun to form a double ridge. In this way, cracking and ridge building have already begun to resurface Connemara. In other places on Europa, chaotic terrain has been covered by ridges to varying degrees, including many cases where the chaotic terrain is barely recognizable under the crisscrossing ridges. Ridge formation is as effective a resurfacing process as chaos formation. We saw terrain where ridges had covered other ridges, and where ridges had begun to cover chaos. Ridges cover over what was there before. Chaos formation destroys it. Connemara is an unusually fresh example of chaotic terrain. A targeted, high-resolution study selected it because it stood out so prominently in earlier pictures, and as a result it became the archetype for chaotic terrain. Thereafter, the characteristics of this specific example of chaos were assumed to apply in general. So, chaotic terrain was described as rare and recent. This misconception, a classic observational selection error, became one of the widely canonical results of Galileo's imaging. In fact, most chaotic terrain is much older than Connemara, and modified by subsequent resurfacing. The older examples of chaos are harder to see, which led to the false impression generated early in the Galileo mission that chaos is a relatively recent phenomenon. On the contrary, like tectonic processes, chaotic terrain has formed throughout Europa's geological history, as far back as the record goes. Connemara is only a typical example of fresh chaos, not European chaos. It must have formed recently relative to the rest of the surface, given that Europa's surface is less than 50 million years old. Connemara probably formed within the past million years, due to the lack of craters. Two examples, each a couple hundred meters across, lie on a raft near the far left. Based on their relationships with other craters, these are probably part of the large population of tiny secondary craters, formed by debris ejected by the rarer, larger impacts on Europa. Returning to chaotic terrain, not only is Connemara not typical of the Chaos Age, but at 80 kilometers wide, it is not typical of the size of chaos patches either. The largest single patch we have examined in reasonable resolution images is roughly circular and about 1,300 kilometers across. Other larger chaotic regions are evident in the dark splotches in the global images. The distribution of sizes of patches of chaos is such that the smaller they are, the more they are, down to sizes so small they are barely recognizable. Evidently, the numbers are limited because we do not have adequate imaging to see the smallest patches. Here, the lumpiness of the texture is finer in proportion to the small size of the chaos area. There are no rafts large enough to reveal older terrain. The patch of chaotic terrain is bulging upward, Some interpretations attribute this feature to the upwelling of magmas, such as slush or viscous ice, which rose and spread across the surface. However, such bulging would also naturally follow from the same fluid exposure that appears to have created Connemara and other chaotic terrain. After the melt-through from below, buoyancy would bulge up the surface during refreezing. The dark, spread-out glow around the small chaotic area on Europa's surface is important because it helps us understand why these features look the way they do at low resolution. And it clears up a common misunderstanding: that the size of lenticular, the low-resolution spots, can indicate the size of chaotic terrain patches. This halo is a lenticular, just as the similar darkening along the major ridge complex shows double dark lines, forming a so-called triple band. The scale, the amount of darkening, and the diffuse appearance are nearly identical, whether the darkening is a halo around a minimal patch of chaos, or a pair of dark margins along a global ridge complex. Once we understand how things look in both global and regional images compared to this clearer view, we can figure out what the old classification system for the earlier, lower quality data really means. The splotches, or mottled terrain, are chaotic terrain. Triple bands are large ridge areas with soft dark edges. Bright plains are areas with many ridges. And lenticular are small chaotic patches made larger by their soft, dark borders. The splotches, or mottled terrain, are chaotic terrain. Triple bands are major ridge complexes with diffuse dark borders. Bright plains are densely ridged terrain, and lenticulars are small patches of chaotic terrain enhanced in size by their diffuse dark halos. Europa's surface is young and appears to be continually resurfaced by two dominant processes: tidal stress forming cracks, ridges, and related tectonic features, and tidal heat creating chaotic terrain. The area sampled encapsulates Europa's fundamental character: densely ridged terrain surrounding a small patch of chaos that appears to be a melt-through site, including a raft of displaced ridged terrain. While this patch of chaotic terrain is similar, we can probably rule out subduction as a major process on Europa. Wherever it occurs, each dominant process, stress and heat, wipe out what was on the surface before. This resurfacing is rapid and recent. Each involves the interaction of the liquid ocean with the surface. These processes, and the conditions they produce, may create and maintain various habitable niches capable of supporting life. Tides drive all of this activity, as we shall see. Despite strong evidence for this picture of Europa doing science, in the words of Galileo. In a legal or humanistic discussion where truth is subjective, one might trust the subtlety of mind, readiness of tongue, and comparative expertise of writers, expecting the best to make the most plausible arguments. However, one must not defend error in the physical sciences, where conclusions are true, necessary, and independent of human preferences. Galileo, 1632. The important surface features and the processes that formed Europa's lines all involved an ocean linked to the surface through a thin, permeable crust of ice in various ways. Narrow cracks allow ocean water to flow to the surface and form double ridges. Cracks have often spread open, filling with fresh ocean water. Occasionally, and from place to place, local heating has thinned the ice, often exposing the ocean and creating chaotic terrain. The images themselves do not show those things happening. I want a video camera on Europa, but we only have snapshots. Those images don't show heat. They don't show ocean water reaching the surface. They don't show plates moving. Although those images culminated in a wonderful engineering project, they were only the start of science. Unsurprisingly, most people perceive science as a body of knowledge, given its predominant presentation in schools. But really, science is a process. The things that scientists do. Doing science gets us from the images sent by a robot camera to understand the character of Europa. So when I describe the melting, the cracking, and the multiple ways that ocean water reaches the surface, I report what we learned by doing science and following various lines of evidence and inference. This process led me and my students and colleagues to the permeable nature of Europa's icy crust. But if science is a process, it is a human one. There is rarely complete agreement and often bitter controversy. People have widely promoted an entirely unique interpretation of Europa from ours. The images remain unaffected by the ocean's isolation from the surface. Instead, all the activity occurred within a thick layer of ice. The idea is based on the fact that, given enough time, even solid materials can. On Earth, the movement of glaciers shows that solid ice flows easily. Even rock has deformed into seemingly improbable shapes over the eons. So, according to the isolated ocean model, the chaos, ridges, and everything else that we see on the surface of Europa resulted from low-density blobs of solid ice flowing up through the crust. The problem is that the logical chain from observations to the isolated ocean model has, on close inspection, weak or missing links. Nevertheless, the isolated ocean model received widespread reporting and acceptance during the Galileo mission's orbit around Jupiter. Thanks to the peculiarities of the power structure within the scientific enterprise, there remains a strong impetus for those beholden to the NASA space mission establishment to pay homage to that model. On the other hand, recognition of the direct role of the liquid ocean in shaping the surface has developed more slowly and recently. It is widely accepted, even obvious, to scientists who can operate more independently or are free to express their views. And even the hardline isolated ocean people are starting to hedge their bets. But it has been a long, hard fight for me and my students. Where did the isolated ocean model come from? To a large extent, it was the result of history. Nobody anticipated that the water on Europa would be anything other than solid ice until 1979. Then, only a few days before Voyager arrived at Jupiter, theorists predicted substantial heating of the Galilean satellites by the friction of tides. The timing was perfect, because the Voyager images immediately showed active volcanism on the satellite Io, which could only be explained by the tidal heating. On Europa, the tidal action effectively maintains nearly all the water in a liquid state, except for a thin layer of ice at the surface. However, at the time of Voyager, any liquid water so far from the Sun seemed a radical notion. To make a credible case, the theorists needed to show that a liquid layer would be possible with even a minimal amount of tidal heating. Thus, conservative estimates of heating rates dominated the scientific literature, allowing only a thin liquid layer under a thick ice crust. The thickness of the ice layer on top of the ocean depends on the rate of internal heating. We know that heat radiates into space, keeping the surface cold, about minus 170 degrees Celsius. But tides continue to generate heat inside Europa. Most rigid materials transport heat by conduction. Conduction carries heat through a pan from your stove to your eggs. If Europa's ice is the same, the faster the heat is produced, the thinner the ice must carry it away. In fact, the thickness of the ice adjusts itself according to the heating rate. If the ice was excessively thick, the internal buildup of extra heat would cause the bottom of the ice to melt until it reached a balance. Excess heat would radiate away quickly if it were too thin, and the ice would thicken. Each 10-meter square patch of ice would conduct out heat equivalent to a 50-watt light bulb for the highest imaginable heating rates. In that case, the ice would adjust to being 1 or 2 kilometers, roughly a mile, thick. More modest heating rates would mean proportionately thicker ice. For example, 10 watts generated under the same area would yield an ice thickness of 5 to 10 kilometers, roughly 5 miles. See a kilometer. So we can see that conservative estimates of the amount of internal tidal heating would tend to imply relatively thicker ice. Convection, rather than conduction, could transport heat through the ice, strengthening the trend. Convection typically occurs in fluids like our atmosphere during turbulent weather, where warm air rises to carry heat and cool air descends. Solid ice can flow too, so convection could be possible within Europa's crust, speeding the transport of heat. Such convection would not kick in unless the ice were thicker than about 20 kilometers. If it did, then the ice could be thicker than it would be with simple conduction. If you guess conservatively, the ice is tens of kilometers thick. In fact, such a thick crust could transport heat almost as fast as a thinner layer if the ice were convecting instead of just conducting it. Remember, even solid ice can flow, albeit slowly. For convection within the solid ice crust, warm ice would flow and cooler ice down, transporting heat like a conveyor belt. If the ice crust was 20 kilometers thick or more, and convecting, it could transport heat as quickly as a crust less than 10 kilometers thick, conducting the same heat. Ice thickness estimates for a given heating rate depend on whether it is convecting. Theoretical considerations suggest that convection may require the ice to have exceptional material properties, such as just the right grain size. We can only speculate whether the ice meets the very tight requirements. Some geophysicists think it is unlikely. If the ice is less than 15 or 20 kilometers thick, the thermal instabilities needed to drive the conveyor belt of convection cannot develop. Thick ice is necessary, though not sufficient for convection. If the crust is convecting, it must be much thicker than if it were conducting heat. As the Galileo spacecraft approached the Jupiter system in the mid-1990s, conservative estimates of tidal heating dominated the scientific literature. Their popularity was not necessarily because the authors believed in the lower heating rates, but because the credibility of an ocean depended on their avoiding the appearance of extreme assumptions. Even as the possibility of a liquid layer under the ice began to be accepted, the more extreme idea that nearly all the H2O might be liquid remained radical. Scholars have investigated the possibility that the ice layer could be sufficiently thin to connect the ocean to the surface. Moreover, some of the Voyager images had shown clear evidence that plates of ice had shifted position. However, the view that Europa's crust was thick and solid was prevalent. There is nothing wrong with approaching new data with such a paradigm in mind. Like all scientists, planetary scientists are agile thinkers, used to confronting new data and debating new ideas with open minds. The problem is unusual access to resources, prestige, and influence within a large space mission. So the stakes are unusually high, and the game attracts players with complex motivations. I was not surprised that the politically powerful dominated the initial interpretation of Galileo's images. The surprise was how quickly it gelled into a party line, requiring adherence to the thick ice paradigm. The Galileo imaging team comprised a wide range of experts in planetary science, providing them access to the project's resources and prestige. Not surprisingly, the more politically skillful, aggressive, and powerful scientific community members ensured they were on board. The dozen scientists on the team were employed by various academic or quasi-academic institutions with which NASA contracted for their scientific expertise. Several team members had broad power bases that extended far beyond the imaging team. They strongly influenced NASA's funding decisions, policy, publications, and public relations. Their loyalties were to themselves and their universities or research institutions. Personal motivations varied, but the prizes were scientific recognition, research money, and influence. NASA got what it needed because the team members' interests and NASA's converged where it was important. The mission's success was crucial for everyone, ensuring the capture of pictures and the reporting of intriguing discoveries. However, where their objectives diverged, each team member had an agenda. The word team was a misnomer, something I gradually realized during my 26 years as a member. The NASA-selected team leader was Mike Belton, a Kitt Peak National Observatory astronomer. Most people involved with the project think he did a good job. The camera got built, the pictures were taken, press conferences were held, and scientific papers were published. However, Belton had to accomplish all those tasks while maintaining a low profile. He had to give the most powerful prima donnas what they wanted to keep the team from blowing up and retain some semblance of control. Those prizes included Jupiter's satellites. The people who planned each picture-taking sequence were given exclusive rights to interpret the data in those images during the 20 years between the start of the Galileo mission and the spacecraft's imaging. If a team member could get the planning assignment for a particular moon, he could take charge of the science. This system explained the odd events at a team meeting in Washington, D.C. in the mid-90s. Image planning for Europa had been assigned to two notoriously powerful geologists, Ron Greeley, Arizona State University, and Jim Head, Brown University. Similar to how Spain and Portugal divided the New World, Head and Greeley divided control of Europe by alternating responsibility for its encounters. Head's students and assistants would plan imaging for one flyby, Greeley's would do the next, and so on. They divided control of the surface and its scientific interpretation by picking different areas to image. At the DC meeting, they complained that they needed help because the job involved so much work. I had some terrific students helping me at the University of Arizona, so I volunteered to do some planning work. My offer was roundly rejected. Greeley and Head were more interested in getting NASA to send more money to their universities than splitting the planning duties. Those who controlled image planning won considerable dividends. They received large amounts of money from their universities because they made the case that they needed to hire a staff of graduate students, research associates and technicians to do the work. The overhead funds with large research contracts are currency for establishing a professor's clout within the university, which translates to salary, office size, prestige, and political power. Another benefit was that these people controlled the scientific results and interpretations that would be presented to the public and the scientific community in the name of the Galileo project. Their initial impressions of the images of Europa, and more frequently the quick-look qualitative impressions of their graduate students and young postdoctoral assistants, were preordained to become the canonical interpretation of the character of Europa, widely accepted as fact. Yet given how the canonical view developed, it should not be surprising that it is wrong. The canonical view relied on initial qualitative impressions due to contractual obligations to make swift and definitive pronouncements. A small subset of the team controlled the process, primarily geologists with prior experience with solid rocky planets. They delegated the interpretative work to their inexperienced students. They locked out other team members with the complementary expertise necessary to do the job right. All of their actions resulted in inexcusable errors in research methods and results. Even at its peak, applying the scientific method is far more complex than the idealized sequence of steps school children must adhere to for their science fair projects: selecting a topic, formulating a hypothesis, designing an experiment, documenting data, and summarizing conclusions. It never works out that way. With multiple researchers competing in the same arena and unanticipated screw-ups at every turn, things proceed in a much less organized way. Moreover, there is considerable variation in science practice from one field to another. The methods and habits of mind developed for geology are based on centuries of experience with detailed observations of the surface of the Earth. However, information about the surface of Europa came from images taken of an alien planet using a telescope flying through space. We can learn a great deal from such pictures, But if the traditional geology techniques are used without attention to the unusual subject and novel sources of information, they can lead to trouble. And they did. Use qualitative analogies, a standard geology technique that interprets new discoveries based on experiences with similar features or structures. This approach has served the field well in exploring and understanding the Earth. But there is a danger in unduly applying terrestrial experience to Europa, which may have entirely different conditions. The initial considerations of Europa were based on comparisons with the most similar types of familiar geological features on Earth. People inevitably interpret the surface in terms of processes that operate on solid planets like Earth. The role of an underlying ocean would not weigh heavily in such thinking. Another problem has been that geological tradition does not address the crucial issues regarding how data about Europa were obtained. In geology, there is usually a glut of data. Researchers walk, crawl, and climb over their subject, chipping it with hammers, magnifying it under microscopes, and even tasting it. Traditional geology must address the challenge of reconstructing and interpreting the processes that led to the observed phenomena. There is too much data. The issue is recognizing underlying patterns and generalities and discriminating between seemingly minor details that are critical constraints on the big picture and local anomalies of no broad significance. However, with Galileo, we have too little data, not too much. The problems with this kind of data are better known to astronomers than geologists. The remote sensing involved, the dependence on image data, the sparseness of the data, and the varying circumstances under which they were obtained, all produce observational selection biases. This bias refers to unavoidable circumstances in the observations, not a failure of the scientific process. Quantitative corrections for such biases are a standard part of data analysis for astronomers. Astronomers understand bias corrections as essential before any interpretation can occur. Unfortunately, the initial interpretations by the dominating geologists of the Galileo project or their students did not consider bias effects. People confused differences in lighting and image resolution with actual surface characteristics when classifying features. The ease of recognizing certain features during a brief look was taken as a measure of their greater physical significance compared with features that were just as real but harder to see. Generalizations were made based on appearances in specially selected locations. Anecdotal impressions became reported facts. Ultimately, in the rush to publicize and publish the initial results of Galileo imaging, several factors came together, driving Europa's geology to be described in terms of thick ice over a largely irrelevant ocean. Various pre-Galileo estimates that an ocean, if any, would be covered by thick ice, a dependence on forced analogies with familiar features and processes on the solid Earth, an insufficiently quantitative analysis of the data, tight control of the quick-look interpretation of Galileo data, which limited interdisciplinary consideration so that only a narrow perspective could dominate. Despite their shortcomings, these early qualitative impressions were prominently published and widely presented by the chosen few at scientific conferences, each wearing the mantle of authority over this major mission. Those graduate students assigned to image sequence planning were appointed as experts on Europa. Magazines for science professionals, especially Science and Nature, fast-tracked the publication of the preliminary interpretations. NASA's publicity machine disseminated the same story. The party line was intensified by active promotion, frequent repetition, and citation. Even though those interpretations were based only on preliminary first impressions, they quickly became canonical facts. Rather than being fast-tracked into the canon, such quick-look results should more appropriately have been treated with extra skepticism. This rule is especially important for Europa, where the images show landforms that might come from very different processes than what we know, where the data is complicated and needs careful analysis of how observations were chosen, and understanding the results requires detailed theoretical research. Early reports from the Galileo imaging team did not fully understand these issues. Nevertheless, the isolated ocean interpretation became the canonical model of Europa early in the Galileo spacecraft's 7 years in the Jupiter system. Canonical doctrine has been known to hinder scientific progress before. Resisting the canon usually involves costly sacrifices by those who follow scientific evidence beyond the boundaries of acceptable belief. In fact, Jupiter's moon, Europa, played a central role in the case that paved the way for modern scientific inquiry during the European Renaissance. For over 1,000 years, the Ptolemaic theory of celestial motions had been a very successful model of the heavens. Every moving body in the sky was deemed to be in orbit around the Earth. These orbits were approximately circular, but they also involved epicycles, ad hoc corrections in which the bodies followed small circles around points that orbited the Earth. With these epicycles, still useful in modern celestial mechanics, this ancient model fits the observational data perfectly and effectively predicts the movements of stars, planets, and the moon across the sky. That theoretical model also had a huge amount of political traction. Envisioning the Earth at the center of everything appealed to anyone contemplating his place in the universe. It certainly must have seemed correct. After all, the ground appears quite still, with the stars and planets whizzing around the sky daily. And more importantly, having the Earth at the center was perfectly consistent with a literal reading of the biblical description of the relationship of the heavens to Earth. Unsurprisingly, this worldview was considered obligatory by the Western religious power structure. The alternative model developed by Copernicus in the early 16th century did not have much going for it. For one thing, it was no more accurate than the Ptolemaic paradigm. Having the planets orbit the Sun rather than the Earth made things simpler. Fewer ad hoc epicycles were needed than in the Earth-centered model. However, the intellectual community at the time had not yet decided whether simpler was better, although that broad question had been a philosophical issue for some time. A far larger problem overshadowed the merits of simplicity. Just as most modern US planetary scientists get their research funding from NASA, and only if they stay close enough to the mainstream, Copernicus was funded by the Church, the same institution that promoted the Ptolemaic paradigm. No wonder he was reluctant to publicly publish his results. Of course, in those days, he was in serious danger. Today, there are cuts to jobs and funding. That kind of career damage had befallen William of Ockham in the early 14th century. Ockham faced expulsion from Oxford due to his radical philosophy and frequent conflicts with the papal court. Ockham's most enduring and influential philosophical contribution is Ockham's razor. The idea is that of all possible theoretical models that could be constructed to fit observations, the simplest one that shaves off non-essential details is best. It is the one most likely to describe the essential underlying mechanism. Clearly, there is no guarantee that a simple model will be more correct than a complicated one. Sometimes, a natural system can be so complex that an overly simplistic model fails to capture the situation's essence. However, experience has shown the power of Ockham's principle throughout the scientific age. Ockham's razor underlies most theoretical modeling in modern science. The medieval church hierarchy in the 14th century was prescient in recognizing the threat of Ockham's ideas to canonical doctrine. Some 200 years later, Ockham's principle valued the Copernican model's strongest asset: its elegant simplicity compared with the Ptolemaic model. In modern physics and astronomy, we often overlook Ockham's razor, making the strength of Copernicus's elegant model apparent. However, during the 16th century, acceptance of the Copernican model was slow. A widely accepted older paradigm seemed adequate, and a powerful establishment opposed change. Then, as now, being right did not necessarily count for much and was often a liability. Surprisingly, the observations that ultimately shifted scientific opinion favoring Copernicus had nothing to do with the contentious planet's orbits around the Sun. Instead, they involved celestial bodies that were unknown to Copernicus. The great astronomer Galileo Galilei discovered the 4 largest moons of Jupiter almost 70 years after the death of Copernicus, and almost 400 years before the Galileo spacecraft imaged those same satellites. Galileo named these bodies in honor of his funding agency, the Medici family. But that was not enough to keep him out of trouble with the Church. If these bodies were not part of Copernicus's model of planetary motion, how could the observations support the model? According to Galileo's 17th century imaging data, the satellites clearly and obviously orbited Jupiter. He had shown by direct observation that not all astronomical bodies orbit the Earth. He had not shown directly that Copernicus's model was correct, but he did provide collateral evidence that it could be. That contribution changed the prevailing mindset and allowed people to think about Copernicus differently. The canonical authorities were not pleased. We now know these 4 moons. The Galilean satellites Io, Europa, Ganymede, and Callisto. Once discovered, the Earth-centered canonical paradigm was overturned, and the door was opened to acceptance of the Copernican worldview. Beyond that, the Copernican description of planetary motions led science much further. It formed the observational basis for the development of Newtonian physics. This demonstration of how simplicity can bring a profound understanding of physical principles gave legitimacy to Occam's principle. It formed a template for modern science's interrelationship between observation and theory. In the sciences, the same forces that resisted the Copernican revolution are still with us. Canonical models are challenging to shake, partly because they are usually based on substantial bodies of evidence acquired over a long time by many researchers. Moreover, inertia always favors an entrenched paradigm. And the politically powerful, by definition, have a strong stake in the establishment position. As a result, there is a strong disincentive to resist the canon, especially for the young and untenured. For these reasons, like all canonical beliefs, Europa's thick ice, isolated ocean model has advocates among the powerful and followers among the weak. They could be correct, but the mounting evidence suggests otherwise. Images of Europa from the 20th century Galileo, a robotic spacecraft, were also viewed in the context of their times. The idea that the ocean was close to the surface was radical. They hastily claimed the ocean had little to do with the surface because the ice was thick. The canon quickly solidified. The organizational structure and policies of NASA's space program and the Galileo mission also worked against innovative thinking. Galileo was a costly project. Failure was not an option. The appearance of continual success was essential. It was not likely that Congress or the public would pay for a second try. Therefore, there was a strong incentive to follow past practices. Unfortunately, as I was to learn, this culture of resisting new ideas permeated all aspects of the mission. I wasn't very knowledgeable about how these things worked when I was selected in 1977 to join the solid-state imaging team. Solid-state imaging, SSI, is a technical term for digital cameras. When the Galileo project started, it was known as the Jupiter Orbiter with Probe, JOP. Shortly afterward, it was named Galileo. The mandatory 3-letter acronym, GLL, began to appear in memos. I became a member of the GLLSSI team. There is also a subtle difference between the Galileo mission and the Galileo project. The mission refers to the overall NASA program managed at NASA headquarters in Washington, D.C. The Galileo project was the development and operational activity managed by the Jet Propulsion Lab, JPL, under a contract with NASA. Typically, JPL's top project management used the word project as a proper noun. When JPL engineers assigned to Galileo said, "The project has determined that we cannot do what you asked for," they meant their bosses told them not to do it. Finally, while the GLL camera was called SSI, the camera on the Cassini mission to Saturn is called ISS, or Imaging System. In October 1977, I attended the kickoff meeting of the Galileo project at JPL in Pasadena. A banner across the front of the room proclaimed, "May the Force be with us," marking the period. The first Star Wars movie had just been released. It was very exciting to be at what I thought was the frontier of science and technology. I was wrong. To guarantee success, the project needed to stay as far back from the frontier as possible to ensure the technology worked. When failure is not an option, neither is innovation. When Galileo finally launched in 1989, its technology was outdated. CCD cameras and computers, more capable than those on board, had already become consumer commodities. Indeed, extreme and unpredictable delays in the launch schedule caused the flight technology to lag significantly behind the times. Originally, NASA planned to launch Galileo from the Space Shuttle in 1982. Having already sold the shuttle idea to Congress, NASA needed to find some use for it. So they dismantled the infrastructure for the Titan Centaur rocket, the old reliable workhorse for interplanetary launches. At the time of the 1977 Galileo kickoff meeting, the plan was to use the shuttle. But no one knew how the space probe would get beyond Earth's orbit once the shuttle got it that far. Eventually, after considerable corporate lobbying in Congress, a modified version of the Centaur upper stage was selected to fly on the shuttle along with Galileo, to propel the probe toward Jupiter. Selecting and developing the upper stage rocket substantially delayed the mission. Galileo's voyage did not begin until 1985, and then it was only a road trip along Interstate 10 from Southern California to Florida. As Galileo was resting at the beach in Florida at the beginning of 1986, waiting their turn for a shuttle launch, everything changed with the explosion of the Shuttle Challenger. In addition to the delays inherent in checking out and re-establishing the shuttle program, it became clear that a bomb as big as a modified Centaur rocket would not be allowed to ride along with humans on the shuttle. The whole strategy for getting Galileo to Jupiter had to be reworked. So the next leg of Galileo's journey was not toward Jupiter, but instead back over the WAM-10 highway to California. As Galileo waited in California again for the next several years, civilization marched on. The shuttle program was reinstated. A weaker, inertial upper stage rocket was developed to propel Galileo onward. And Galileo's once advanced on-board technologies became dated relative to consumer commodities. Galileo traversed America 3 times before the shuttle Atlantis launched him from Cape Canaveral in late 1989. The inertial upper stage was so weak that extra encounters with Venus and the Earth were needed to give gravitational kicks to the craft at the expense of doubling the travel time to Jupiter. The bundle of shop-worn 1970s technology reached the Jupiter system late in 1995 and didn't complete its mission until 2003, more than a quarter century and 4 more Star Wars episodes after the kickoff meeting. Call me superstitious, but that 1977 Star Wars banner was asking for trouble. Even if Galileo had gotten to Jupiter on its original schedule in 1985, its technology would have been old. During the project's first years, as I listened to the reports and discussions at endless imaging team meetings, the selection of components generally required that they be available in commercial catalogues. I was disappointed to learn I wasn't as tech-savvy as I thought, but it made sense. Anything that flew on the spacecraft had to work, which meant it needed a track record. But what was disappointing and inexcusable was how this caution pervaded all aspects of mission planning, extending even to planning for the science analysis that would be done here on planet Earth. What well-managed enterprise would specify technology purchases and functionality 5 years into the future based on what was already available on the market? I didn't realize this reluctance to adopt cutting-edge technology until 1980, primarily due to the Hunt brothers' attempt to dominate the silver market. Photographic prints, that is, photos developed and reproduced on paper, are made with silver. Mission planning in the late 1970s included considering the production and distribution of the pictures the spacecraft would take when it got to the Jupiter system. For budgeting picture production, planners estimated that 100,000 pictures would be taken, and each would need to be printed in a few different versions with varying contrast, brightness, sharpening, and other enhancements. All these large format pictures would need to be distributed to all the imaging team members and various archives. You can do the arithmetic. The project would need millions of prints. By the time the Hunts bought up half the world's silver supply, the Galileo darkroom budget had soared to $12 million. Several things about this plan impressed me. The first was the expectation that the spacecraft could capture many more pictures than the budgeted 100,000. The spacecraft's durability and the speed of radioing back digital images would not limit the number of pictures. Unbelievably, the staggering printing costs would limit the number. I was also impressed by the dollar budget. With 12 team members, the mission would incur substantial costs for photo printing. Obviously, this plan was not how I would spend my share of the resources. Last but not least, I found it difficult to imagine conducting science using thousands of large format photographic prints. The mere physical manipulation seemed mind-boggling. I could hardly imagine organizing or analyzing them systematically or quantitatively. Nevertheless, the plan adhered to the established space mission tradition. The plan involved radioing the data bits back to Earth. Each image was to be composed of 640,000 measurements of brightness in the camera's field of view, arrayed in a field of 800 by 800 pixels. The brightness values were encoded as 256 levels of gray, so each image could be encoded as 640,000 bytes, or about 640 kilobytes, 2/3 of a megabyte, or a few times less, with data compression schemes. A central processing facility on Earth would spend $12 million converting that information into photographic hard copies for delivery to the science teams. Once the hard copies were printed, the original data bits would be stored on magnetic tape, which would be hard to access because the tape is cumbersome to manage and vulnerable to physical deterioration and data loss. Following the time-honored convention, the photographic hard copy would be considered the final, permanent product. As a medium, photographic vinyl copy has some advantages. The printed resolution can be very high. You can quickly look over many images spread across a table. No special viewing equipment is needed, and they can be tacked to a bulletin board. However, compared with digital information, printed photographs have several disadvantages. A photographic print cannot display the full range of brightness and contrast contained in the original digital data. Using, and then archiving, hard copy rather than the original bits means throwing out a good part of your expensive and valuable information. Printing the hard copy will limit further enhancements. Even worse, automated routines used in most photographic processing may obscure the most valuable scientific data. The unexpected. In 1979, I observed the processing of Voyager images. A team of skilled craftsmen from the US Geological Survey was detailed to JPL, using sharp knives and glue to cut and paste photos into large mosaics. Although these individuals were highly skilled and diligent, their work seemed more reminiscent of the Second World War era than the modern era. Information technology. The Voyager encounter with Jupiter's satellites hindered scientific interpretation because it relied on printed-on-paper images. For example, when the Voyager imaging team received the first photos of satellite Io, they were mystified by its appearance. The photos showed a strange, blotchy place that looked unlike any planetary surface they had seen before. The explanation was clear in the data sent to Earth, but it was lost when the photos were printed. Fortunately, the optical navigation team received different versions of the same images. We gave those engineers overexposed high-contrast versions because they needed to see the stars in the camera's field of view to navigate the spacecraft. Io appeared only as a white disk, but it was this overexposure that allowed an optical navigation engineer at JPL, Linda Morabito, rather than an imaging team scientist, to discover volcanism on Io when she spotted the gigantic volcanic plumes spraying into the dark sky. The information for both image versions was in the original digital bits sent by Voyager, but any single print could only show part of the story. When the Galileo imaging team was planning its photo budget, computers were already used elsewhere to display and process images. The field of digital image processing was still in its infancy, but its potential was clear. The commercial sector, already active in Silicon Valley, was developing applications poised to revolutionize image processing in all fields, especially where the money was, in biomedicine and defense. But on the frontiers of planetary science, revolutionary digital image data, radioed hundreds of millions of miles from Jupiter, were being processed using 19th century technology. Galileo's $12 million plan for the future aimed to continue this trend. I decided to let the Hunt brothers keep my share of the silver. I would be happy to forego any hard copy if the Galileo project sent me the bits of information when they arrived on Earth. All I asked in exchange was that I might get part of the $1 million savings from my share of the darkroom expenses to buy image processing computer equipment. The advantages seemed obvious, at least to me. The project would save money. I could buy a fantastic computer system, and by waiting until I needed it, I could buy an even better and cheaper one. I would not have to manage a giant library of photographic hard copy in my lab, and I would have the digital bits to look at any way I wanted to. Moreover, I can take precise quantitative measurements more easily than paper photos. This approach might work for others on the team as well. I presented this idea at a team meeting in Hawaii in 1980. It did not go over well. The reasons seemed incredible then and are even more incredible in retrospect. For instance, a geologist struggled to comprehend the process of making measurements on a digital image. He was unable to envision modern graphical measuring tools on a computer. He thought my proposal would require him to lay a wooden ruler against his computer monitor. The old-timers could not imagine changing their ways. Everyone reacted negatively. As events later unfolded, I understood another underlying reason for the embarrassing reception. The broad distribution of resources implicit in my vision could only upset entrenched interests. My idea was roundly mocked and rejected. But I learned an important lesson. New ideas are not necessarily welcome at the frontiers of planetary exploration. My plan was at odds with another aspect of the Galileo mentality. The planning process had no way to accommodate the rate of change in technological advancement. The 1985 plan relied on computers from a 1980 catalogue. The same went for data storage media. My plan was attacked because it would require rooms full of computer tapes to store the data at each of our home institutions. No one bought my prediction that a few laser discs could hold the Galileo data set on a single bookshelf. Actually, this was not a radical idea. Video discs were already on the commercial market, and the CD format was in the works, but such notions were too risky for Galileo. In short, the project was as conservative in planning technology for my office, which was to be bought years later, as they planned for the technology to fly into space. Had I comprehended the politics and mindset of the project and imaging team, I would have refrained from speaking. Being right did nothing good unless you kept it to yourself. Sharing good ideas was definitely a mistake. Naturally, the project had to abandon its traditional methods as technology advanced. The world was adopting digital imaging. Image processing could be done on home computers, and the Galileo dataset could fit in a sun visor CD caddy. I now have all the images of Europa on a single CD. Eventually, the imaging team adopted my plan, except that somehow, as the money flowed, some team members were more equal than others. The same resistance to change that affected the use of technology also permeated the imaging team's way of doing science. The scientific, isolated ocean paradigm was embraced for Europa, because any other interpretation would have suggested a high-profile commitment to something new. Authorized speakers propagated a mantra of questionable facts, and anecdotal evidence selected to bolster the model. The isolated ocean model became the widely accepted dogma of the Galileo mission. At the same time, that paradigm was becoming entrenched, and a less rushed interdisciplinary review of the data showed that what is seen on Europa differs from much of what had been reported earlier. We discovered some key anecdotal evidence from the previous quick look, which was unreliable. Significant observational selection effects were emerging, allowing for quantitative corrections. An interdisciplinary approach. On Earth, twice each day, tides wash up over beaches, flow in and out of estuaries, and fill and empty harbors. At low tide in New Brunswick, Canada, water drips onto the beach from wet seaweed on cliffs 16 meters above. Yet there are no discernible tides in the Mediterranean, and sailors crossing the oceans see no tidal effects. From human experience, we tend to think of tides as a local phenomenon, where twice daily the ocean rises and falls against the land. But on Europa there is no land. How can tides exist with an ocean 150 kilometers deep, covering the globe? Tide effects are very different from a whole body point of view. The tidal effects at a particular beach or harbor are simply a detail of the global picture, as diverse as the tides seem from a local or regional perspective. We can understand them by thinking on a global scale. The self-gravity of a planet tends to make it spherical. Each bit of mass pulls on each other, with their cumulative gravity pulling the material into a symmetrical ball. The strength of the material can support some deviations from the regular global shape dictated by gravity, but not much. Eventually, shaking and erosion allow gravity to pull mountains down toward the planet's center, continually working to keep the planet round. Tides come into the story when we consider that no planet is alone. Besides self-gravity, any neighboring body also exerts forces on each bit of the planet's mass. Our moon acts on the Earth, for example. The force of gravity depends strongly on distance, so the moon pulls more strongly on the part of the Earth nearest to it, less strongly on the center of the Earth, and even less strongly on the mass of the Earth, on the side farthest away. The moon stretches the globe of the Earth, elongating it into an oval. More precisely, the three-dimensional version of an oval, an ellipsoid. What matters for this stretching is not how hard gravity pulls, but rather how much harder it pulls on one part of the Earth compared with another. The amount of stretching is nearly the same on each side, so the two tidal bulges are equally high. The key is to stop thinking of a tide as a local thing at your boat dock or favorite beach. A tide is a global effect. It stretches a moon or a planet, in this example the Earth, into an oval shape, elongated in line with the other body that causes the tide. Nothing about tides requires an ocean. The whole planet stretches, no matter what it is made of. The rocky body of the Earth stretches under the tidal pull of the moon, although the strength of the rock resists the pull. The watery envelope around the Earth elongates more, but only because it is weaker than the rock. Things get more complicated in the real universe. Every other body, not just the moon, also pulls and stretches the Earth. Fortunately for the folks who have to calculate these things, only one other body makes a significant contribution: the Sun. It acts to stretch the Earth toward itself. So this stretching is in a different direction and in a different amount than the tidal stretching due to the Moon. Even though the Sun is some 30 million times more massive than the Moon, it also is 300 times farther away. These effects balance by coincidence, so it and the Moon stretch the Earth similarly. So at any instant, the globe of the Earth is being stretched in two different directions by similar amounts. Each of those two tide raisers, the Sun and the Moon, tries to mold the Earth into an ellipsoid elongated toward itself. When you do the geometry, the total of those two distortions is also an ellipsoid. However, because the Sun's position relative to the Earth and Moon is always changing, the magnitude and direction of the elongation periodically change. The shape of the Earth continually responds. On average, the surface of the ocean layer is pulled about 3 meters upward at the ends of the stretched ellipsoid. Each of Earth's spherical layers, its metallic core, the rocky mantle, and crust, the atmosphere, as well as the thin water layer, also stretch into ellipsoids, all conforming to the combined gravitational pulls of the Sun, the Moon, and the self-gravity of the Earth. But the Sun, the Moon, and the Earth do not stay still. The Moon orbits the Earth each month. The Earth orbits around the Sun each year. And the Earth spins around each day. The direction and magnitudes of the tides keep changing. The materials of the Earth, the nickel iron of the core, the rock, the water, and the air, are all subjected to ever-changing tidal forces that continually deform and remold them. The planet cannot keep up. The rock that makes up the bulk of the Earth cannot stretch or flow fast enough to keep the shape lined up with the tidal forces. The alignment is always behind where it should be. Moreover, the stretching of the rock never gets nearly as elongated as it would be if it had time to respond. Only the fluid spheres of Earth, the ocean and the atmosphere, can respond reasonably promptly. But the ocean layer is thin, only a few kilometers at its deepest. To change the outer shape of the planet, the water flows to fill in each end of the stretched ellipsoid with an extra meter or so of fluid. The oceans must keep rushing in changing directions as they move around in response to the tidal force. Pesky continents get in the way, even though they cover only a small fraction of the surface. The water flows and sloshes in complex ways as it rushes, trying to respond to the changing tidal force. The flow gets trapped in places funneled into random coastline configurations, like Canada's Bay of Fundy. The water moves especially fast as it passes through the Bering Strait and across the shallow Bering Sea. The Mediterranean Sea is so landlocked that there is little change. Relatively little water can reach Gibraltar. The local effects vary tremendously from place to place, but the tide is a global-scale phenomenon. The continual reshaping of the Earth as its fluid outer layer accommodates the tidal pull of the Sun and Moon. In Europa, the tides are much simpler and larger. Only one tide raiser dominates, and that is Jupiter. It is so massive, 30,000 times the mass of the Moon, and so close to Europa, only about 1.5 times as far as the Moon is from Earth, that its tide stretches the 3,300-kilometer wide globe of Europa by about 1 kilometer. Compare that value with the 13,000-kilometer wide Earth, being stretched by only a few meters. Europa's tide is huge but changes much more slowly than Earth's. Compared with the Earth's oceans, Europa's water layer has an easier time keeping up with the global shape dictated by the tidal forces. It helps that there are no continents or islands or shoals poking up from the rock below, so the water can readily flow to conform to the ellipsoidal global shape. And the ice on the surface is too thin to resist the changing shape of the water layer. Below the ocean, Europa's rocky mantle and iron core also have time to conform by slow, viscous flow to the stretching effect of Jupiter. This tide is nearly constant because Europa keeps one face toward Jupiter. In other words, as Europa orbits around Jupiter once every 80 hours, it rotates at a matching rate. Try this at home. Walk once around a friend, keeping one shoulder toward them. Note that your body will spin around exactly once relative to your surroundings. Such synchronous rotation is common among satellites in the solar system. Our moon, of course, is the classic example. We always see the same face of the moon from Earth. Remember, the tidal force on any moon, due to its planet, tends to stretch out the moon, bulging it on the planet-facing and opposite sides. For any moon in synchronous rotation, e.g., our moon or Jupiter's Europa, those bulges will always be in the same places on the body. The material, rock, water, or whatever, does not need to constantly shift around trying to catch up with the changing direction of the tidal force. That is why Europa's enormous tide, kilometers high, is nearly fixed in place on the body. Europa's body and ocean are stretched close to the shape dictated by Jupiter, and they do not have to shapeshift very much. In fact, if Europa were on a perfectly circular orbit and spinning perfectly synchronously, there would be no variation in this tide. The amplitude would not change because the distance from Jupiter would be constant. The orientation of the elongation relative to the body of Europa would also be fixed, because with synchronous rotation, the body retains a fixed orientation relative to the direction of Jupiter. As huge as this tide is, other than establishing the shape of Europa, it would have no interesting effects. And indeed, most moons are that way. In fact, the reason they are that way has to do with tides. Most moons, including Europa, started spinning in fairly random directions and moving on eccentric orbits depending on the last big impacts during their formation period. With non-synchronous rotation, the moon's material would continually play the catch-up game, and the tidal elongation would never quite be lined up with the direction of the planet. The asymmetry of the shape would allow the planet's gravity to exert a torque, a twisting force, that would eventually force the moon to rotate synchronously. Similarly, it also would tend to make the orbit circular. So, tides are suicidal or self-cancelling. They make spins synchronous, and they make orbits circular. At that point, the tidal shape of the body becomes fixed and constant, boring, exerting no tidal effects at all. The good news from Europa was that the tide is not exactly constant, so some very interesting things can happen. This was good news for me because we celestial mechanicians love to work out these complicated processes. Europa's non-boring tides would be very good news for any organisms in Europa, because the things that tides do might make Europa habitable. So why didn't Europa's tides turn themselves off? Why did the usual boring moontide scenario not occur there? And why did it take so long for people to figure it out? The plot thickens further. The first evidence for something much more exciting than usual came from Galileo's data, from the great astronomer's observations of the moons of Jupiter in the early 1600s. Galileo made careful plots of the movements of the satellites that he saw through his telescope. The orbital periods were quite well defined. The inner three periods are approximately 42.5 hours for Io, 85 hours for Europa, and 170 hours for Ganymede. The ratios of these periods are striking. From these numbers, going back to the original observations by Galileo, it appears that they are locked into an exact ratio of 1 to 2 to 4. In the time it takes Ganymede to go around Jupiter once, Europa goes around exactly twice, and Io goes around 4 times. This ratio also means that the location in the orbit where Io overtakes Europa, where they are both in line with Jupiter, conjunction. After conjunction, Io advances ahead of Europa, and the next catch-up with Europa is at the same location after Europa has made one whole orbit, and Io has gone around twice. The conjunction of Europa with Ganymede also occurs at a fixed location because of the 1:2 ratio of their periods. Moreover, Galileo's plots of the orbital motion also showed that the conjunction of Europa with Io always occurs on the opposite side of Jupiter, from the conjunction of Europa with Ganymede. The scientific world at the time of Galileo found it sufficiently traumatic to deal with the simple issue that the satellites seemed to be orbiting Jupiter and not the Earth, violating canonical wisdom. Understanding the strange and amazing ratios among the orbital periods took almost 2 centuries. The explanation was part of the great body of research by French mathematician Pierre-Simon de Laplace, published early in the 19th century. Laplace showed that the periodic repetitions of the conjunctions of the Galilean satellites enhanced their mutual gravitational effects, although each satellite's orbit was predominantly governed by Jupiter's gravity. The satellites' effects on one another can perturb the orbits in various ways. Whatever effects they have on one another are reinforced by how their mutual configurations repeat periodically every few days because of the remarkable ratios among their orbital periods. This enhancement, due to the periodic repetition, is a resonance. The resonance has several effects. For one thing, it is self-preserving by maintaining the whole number ratios of the orbital periods. Most importantly, this resonance maintains the eccentricities of the orbits. Even though tides tend to circularize orbits, the resonance among the satellites keeps them on eccentric, elliptical paths. Remarkably, though, more than 150 years after Laplace, as astronomical interest in the planets and their moons grew during the 20th century, a misunderstanding led to a widespread belief that the orbits of the Galilean satellites were circular. In nearly every textbook and authoritative tabulation of orbital parameters, the eccentricities of the Galilean satellites were listed as precisely 0. A perfectly circular orbit has an eccentricity value of 0, while the more stretched or elliptical it is, the higher the eccentricity value. The misleading table entries had propagated from a peculiar tradition in celestial mechanics. For satellites in resonance, eccentricity values can oscillate. What was the poor table writer to do? The actual eccentricity at any time would be something different from what the table showed and ever-changing. Given limits on available columns and the need to keep tables simple, only the amount of the periodic variation is often tabulated. For Io and Europa, resonance creates substantial eccentricity values, but the periodic variation is near 0. So, for many decades, astronomers and students were informed by the authoritative reference literature that the eccentricities of these satellites were 0. The true eccentric motion remained unappreciated. One reason that no one was surprised to see the value 0 listed is that tides were expected, in general, to circularize orbits, especially if you did not fully appreciate the resonance. In the mid to late 1970s, I wrote articles about resonances among satellites and gave several presentations about them at conferences. A few weeks before Voyager reached the Jupiter system, I got a phone call from my colleague Stan Peel, a professor of physics at the University of California in Santa Barbara. Stan is a few years older than I, and I had learned a great deal about tides and celestial mechanics from studying his work. This time, Stan had questions for me. He had heard me speak about the Laplace resonance, and he wanted to confirm that, contrary to the common tabulations, the eccentricity of Io was 0.0041, and the eccentricity of Europa was 0.01. Had he understood me correctly when I had said to disregard the tabulated values of 0? I told him that was correct. "Do you know what this means?" he asked. "No, what?" I cluelessly replied. "It means that there must be an incredibly high tidal heating rate in Io and probably in Europa." I became the first of many celestial mechanicians to slap palm to forehead. Why didn't I think of that? As described above, if a satellite's orbit is circular and its spin is synchronous, the tidal bulges become fixed. Even if the bulges are big, they will have no interesting geophysical effects because they are fixed and unchanging. There is no friction and so no heating. But if a resonance keeps the orbit eccentric, the tidal effect increases and decreases during each orbit as the satellite's distance from the planet changes. The body continually changes shape, so there is friction and thus heating. And if the tide happens to be raised by a nearby planet that's the largest in the solar system, a great deal of heat must be produced. A few days before Voyager reached Jupiter in 1979, the magazine Science published an article by Peel et al. That predicted something dramatic would be found at Io and possibly at the other Galilean satellites. The rest is history. Voyager found Io to be actively spewing volcanic plumes into space, and the surfaces of the other resonant satellites, Europa and Ganymede, appeared far more active than frozen ice balls in space had any right to be. Years later, what Voyager had learned about the Galilean satellites was reviewed in a reference book, The Satellites of Jupiter. The dynamics of the Laplace resonance were described, as well as the values and variations of the eccentricities. Once ideas are established, they are hard to change. Ignore what you may read elsewhere to the contrary. Europa's orbit is not circular. Its eccentricity is about 0.01. Everything interesting about Europa follows from the fact that the eccentricity is not 0. Because Europa's orbit is eccentric, tides on its body change throughout each 85-hour orbital period. The magnitude of the tide depends strongly on Jupiter's distance from it. The tide-raising gravitational effect is strongest when Europa reaches its minimum distance from Jupiter, at perigove, which means closest to Jupiter, and is weakest half an orbit later. Europa rotates synchronously so that a flagpole planted on the Jupiter-facing side would point toward Jupiter throughout each orbit. Its maximum distance at apogee. Consider the true proportions of the geometry. Europa's radius is about 1,560 kilometers and averages a distance of 671,000 kilometers from Jupiter, whose radius is about 71,500 kilometers. The average height of each tidal bulge on Europa is about 1/2 kilometer. Europa's orbital eccentricity is enough that Europa's distance from Jupiter varies by about 1%. That small variation in distance means that the orbit is nearly circular, but the variation is enough to drive dramatic effects on Europa. The tide does not only change in magnitude. Over each orbit, the direction of the elongation relative to the body of Europa also changes. The explanation follows from something Johannes Kepler discovered in the early 17th century about the orbits of planets, something that applies to Europa as well. Europa must go extra fast in its orbit around perigove and extra slow around apogee. But Europa's rotation, its spin rate, is constant throughout the orbit. Consider what that means for a flagpole pointing to Jupiter at the pericenter. With the extra orbital speed there, the rotation of Europa is too slow to keep the flagpole pointing exactly toward Jupiter. Later, as Europa approaches apogee, its orbital motion slows down compared with the rotation, which stays constant, and the flagpole catches up again with the direction of Jupiter. The tide always wants to be aligned with the direction of Jupiter, but that direction shifts back and forth relative to the flagpole, and thus relative to the body of the satellite. So the orientation of the tide relative to the body of Europa varies periodically during each orbit, just as the magnitude varies. The body, including its rocky interior, thin ice crust, and thick liquid water layer, is continually remolded in response to these changes in the magnitude and direction of the tide. Understand that the change in the direction of the bulges does not represent the rotation of the body, but rather a remolding of the moon's shape. Every 85 hours at the imaginary flagpole, and simultaneously at the opposite side of the satellite, the height of the surface rises and falls by 30 meters, relative to the average tidally elongated figure of Europa. And between the rising and falling, the high point of the bulge moves back and forth by about 100 meters, from one side of the flagpole to the other. At least, that is how much the shape of Europa would change if the materials could respond quickly to the tidal force. Most calculations show that the thick liquid layer that dominates the outer 150 kilometers of Europa would allow a rapid response. As long as Europa's water is largely liquid, our estimate of tidal variation is accurate. But the tide's magnitude would be much smaller if the water were nearly frozen. If spacecraft ever return to Europa, they may be equipped with altimeters capable of measuring the height of the tide. In principle, these measures could detect the thickness of the ice. Unfortunately, other uncertainties about the internal structure may swamp out the effect of ice thickness. Measurements of tides will tell us whether there is an ocean, but only with very precise measurements and improved interior models. Will there be any hope of using this approach to determine the thickness of the ice? Because the length of a day on Europa, which depends on its rotation period, is very close to the period of an orbit, we call the tidal variation the diurnal tide. I may have introduced that term to Europa science. If so, I regret it, because the periodic changes I described depend more on the orbital motion than the spin. But the name stuck because the period is essentially the length of a day on Europa, and only 3.5 Earth days. Whatever you call it, these periodic workings are responsible for the unique character of Europa, providing frictional heat for melting the water and stressing and cracking the icy crust. Were it not for the eccentricity-driven diurnal tides, Europa would be as inactive as Callisto, the farthest out from Jupiter of the 4 Galilean satellites. Callisto, not part of an orbital resonance, and thus with no diurnal tides, is simply a heavily cratered target for bombardment by every type of debris in the solar system. It is not being changed from within. The 3 resonant satellites, Io, Europa, and Ganymede, all have much more interesting geology and geophysics because of the various effects of the tides. Tides affect the satellites in 4 major ways. First, the continual remolding of the body's figure entails friction and generates heat. We usually think of frictional heating as something that happens when 2 objects are rubbed together. Here, we discuss internal friction, energy dissipation when work is done, and material distortion. Bend a paperclip back and forth and it gets hot. The same happens when the materials of Europa, iron, rock, and ice undergo repetitive distortion by diurnal tides. Europa gets heated from the inside out. Second, the change in shape stresses the material. We haven't got a clue about the effects of this stress in the deep interior, but we certainly see its effects on the ice crust. Imagine trying to change the shape of an egg. The fluid below the surface would not be affected much, but the shell would certainly crack. The same thing happens on Europa. Hour by hour, its shape is changed. The ocean water readily accommodates, but the ice shell must crack, and each crack continually gets worked. Europa's surface undergoes a variety of tectonic processes evident on its surface. Third, as the tidal force changes, the response of the satellite's material slightly lags. So the satellite's elongation is not exactly lined up with the tide raiser. Jupiter? Jupiter's gravity pulls on this ever so slightly asymmetrical mass distribution, in a way that can apply torque, a twisting force, to a satellite's rotation. Europa may not rotate synchronously after all. Fourth, the gravitational torques and torques involving tides raised on Jupiter by the satellites have probably caused long-term variations in their orbits. The Laplace orbital resonance may have changed over time, which means Europa's orbital eccentricity may have been different in the past. Tidal heating and stress directly affect the satellite's observable surfaces. Stress corresponds to observable tectonics like cracks, and heat corresponds to observable thermal features like chaos. The changes in rotation and orbits modify the tides and thus indirectly affect what we see on the surface. These effects exist on all Galilean satellites, but they do not necessarily manifest themselves to the same extent or in the same way. On Io, because it is closest to Jupiter, the tidal heating is so great that volcanism swamps out and hides most large-scale tectonic effects. It is not obvious whether the tectonic features observed there relate to tides. At the opposite extreme, far from Jupiter, poor, pathetic Callisto has no significant tides because it is not part of the orbital resonance. Ganymede shows little indication of heating because it is the farthest from Jupiter of the three resonant satellites. Nonetheless, a substantial portion of Ganymede's surface is dominated by tectonics. Europa lies in the sweet spot between Io and Ganymede, where there is considerable tidal heating, but not so much that thermal effect. Considering the heat of tidal forces, let's start with an overview of Jupiter's four large moons, moving from the closest to the most distant: Io, Europa, Ganymede, and Callisto. Friction generates heat as diurnal tides periodically distort the figure of a satellite. When Stan Peale and his colleagues in 1979 put that old idea together with the long-known orbital behavior of the Galilean satellites, they realized how much heat might be generated within those bodies. For Io, the closest to Jupiter of the four Galileans, the calculations led to their legendary prediction that Voyager images would show major thermal effects. They discovered huge amounts of ongoing volcanism there a few days later. The Voyager images of Europa were less dramatic, but it was clear that this satellite had been geologically active until recently, and there was no reason to believe that the activity had stopped. The contrast between Europa's appearance and that of dead, cratered objects was obvious. Also obvious was the clear trend among the Galilean satellites, correlating the geological activity with distance from Jupiter. The closer a satellite is to Jupiter, the fewer impact craters there are, and the more the geology is dominated by tidally driven processes. Furthest out and not part of the eccentricity driving Laplace resonance, Callisto was the archetype of a dead, bombarded planet. Closer to Jupiter and with a resonance-driven eccentricity, Ganymede displayed large Callisto-like areas. But other broad regions showed tectonics and resurfacing. Closer still was the completely resurfaced Europa. And closest to Jupiter was the spewing Io. Given the great activity at Io, it was natural to calculate the likely effects of tidal heating on Europa, the next satellite in the resonance. The relevant properties of Europa could only be guessed at, especially the parameter Q, which is supposed to represent and characterize all of the diverse frictional effects within the satellite. Q is an engineering and physics parameter representing energy dissipation as heat in oscillating systems. For example, your car's suspension has springs oscillators damped by shock absorbers, dissipating energy from bumps into heat. To make a credible case that something weird might happen within Europa, the theorists needed to adopt very conservative assumptions about the value of Q and everything else that could affect the tidal heating rate. In other words, they needed to show that intriguing things could result with even the minimum likely amount of heat. They found that tidal friction could keep most of the H2O melted, even with such minimal heating models. So, the heat was enough to maintain a global liquid water ocean, a major discovery. However, theorists constantly try to push the implications of their work as far as they can. They realized that without a global ocean, the tidal stretching of the satellite would be small, so the crust would not be stretched much, and there would be much less heating. Therefore, the existence of liquid water seemed to be contingent upon the existence of a global ocean, as any significant liquid presence would imply the existence of a global ocean. Moreover, if an ocean has existed recently, it has existed for a long time. And if it had existed for a long time until recently, it must exist now. It would be surprising if it froze solid just before our spacecraft arrived there. Those early conservative estimates gave heating rates of only about 1,600,000,000,000 watts. While this may seem like a substantial amount of heat in an electric oven, it's not nearly as much when dispersed throughout a body the size of Europa. Consider this. We know the heating has been going on for a long time. So there is a balance between the heat produced inside and the energy radiated from the surface. A similar process occurs in a 100-watt light bulb. The bulb generates 100 watts of heat and emits 100 watts of energy. Given the size of Europa, the tidal heat spread over the entire surface would radiate out at a rate of about 0.05 watts per square meter of surface, assuming the old conservative estimates. 0.05 watts is an amount too small to measure. We have measurements of the heat escaping from neighboring Io, most of which must be generated by tidal friction radiating from a few hotspots associated with the largest volcanoes. We can use that measurement to estimate Europa's tidal heating rate by scaling Io's velocity to account for Europa's different orbit, farther from Jupiter, and size, smaller than Io. We estimate that about 0.2 watts per square meter must be continually removed through the satellite's surface, nearly 4 times the early conservative estimate. Accounting for the likely material properties of Europa relative to Io raises the Europa heat flow even more, to about 0.3 watts per square meter. All that heat must pass through the ocean, ice, and surface. We can calculate how thin the ice must be to let the heat out. First, assume that heat is carried outward through the ice by thermal conduction, like the heat moving out through the side of your coffee cup from the hot liquid inside. The ice would need to be 2 kilometers thick to transport 0.3 watts through each square meter of the surface. If the ice were thicker, heat would build up inside, and the ice would melt until it reached the steady-state thickness of 2 kilometers, which would then conduct the 0.3 watts. In this conductive model, the ice thickness varies inversely with the amount of heat transported. If the internal heating rate decreased, the ice would thicken until the rate of heat transport decreased into a new equilibrium. If the tidal dissipation were as slow as the old post-Voyager guesses, only 0.05 watts per square meter, the ice would be about 12 kilometers thick. Yet even that value is still quite thin compared with the 150-kilometer depth of the ocean. If the ice were converted instead of being conducted, it could transport the same heat more quickly and efficiently. Convection would require the ice to flow vertically, carrying heat up and sinking to pick up more heat. The ability of solid ice to flow in that way depends on the exact required properties of the ice, especially its viscosity, which describes its flow characteristics. But we do not know those properties. Results depend on assumptions. Most estimates require ice thicker than 20 or 30 kilometers for convection. Some quantitative modeling even suggests that any convecting layer would probably be inconsistent with the existence of a liquid ocean, a result that strongly favors the thin conducting ice layer. For a given rate of internal heat production, if the ice layer were transporting the heat out by efficient convection, it would be thicker than if the transport were by relatively inefficient conduction. Thus, either a thin ice model, thinner than 10 kilometers, with conductive heat transport, or a thick ice model, thicker than 20 or 30 kilometers, with convective heat transport, could be consistent with a rate of heat flow in the middle of the range of plausible values. If the tidal heating were near the old low guesses, the ice would be thick enough that convection would have a high chance of being activated, letting the ice be substantially thicker than 20 kilometers. This thickness was the canonical value at the time of Galileo's arrival at Jupiter. As a result, the first accepted explanations of Europa's geology were based on the idea that solid-state convection and other solid-state movements in the ice were the main processes at work. In that view, widely publicized and promoted under the authority of the Galileo project, the ocean would have been isolated from the observable surface and could not play a direct role in the geological processes that shaped the surface. The modeling of heat transport on Europa is too uncertain to definitively discriminate between thin conductive or thick convective ice. Europa's actual current physical condition may depend on its thermal history. If the heating rate has increased toward its current value, the ice would likely be thick and convective. The ice will probably be thin and conducting if the heating rate has dropped from noticeably higher levels. Because tidal heating is driven by orbital eccentricity, the tide-driven history of Europa's orbit may be crucial. Contrary to the official story, what we see on Europa suggests that the ocean has been directly linked to the surface, and that result is consistent with thinner ice than allowed by convection. What first convinced me was the consideration of the observed tectonic features. Remember all those cracks and ridges? To understand them, we must consider how tides stress the icy shell. The history of stress on the icy crust is recorded by the cracks that dominate more than half the surface. This record, as laid out in images, includes the entire geological history of the satellite. However, defining geological history as the period that created the currently visible surface doesn't say much. In fact, the visible surface records only the most recent 1%, or some 50 million years, of the 4.6 billion year age of Europa. Moreover, even during the brief lifespan of the surface we have imaged, the continual slicing and dicing have left an interpretable record covering only the last few million years. Nevertheless, Occam's razor implies that the processes recorded in the most recent tectonics represent the same types of continual tectonic modification that have gone on for much of Europa's history. There is no compelling reason to believe otherwise. To consider how tidal stress would affect the surface, we need to marshal our best understanding of the likely physical properties of the ice. The interior heat rapidly radiates into space, causing the upper part of the ice crust to freeze at -170 degrees Celsius. So this upper portion of the ice is brittle and elastic. Elasticity means that it acts springy, while brittleness refers to its breakability when a certain stress limit, its strength, is exceeded. The ice is much warmer near the bottom of the crust, reaching the melting point, about 0 degrees Celsius, where it meets the ocean. The warmer ice is solid but viscous, capable of flowing slowly like cold honey. A more apt analogy is a glacier, a river of slowly flowing ice. In between, there is a transition from brittle elastic properties near the cold surface to a predominantly viscous character near the warm base of the ice. The behavior of the ice also depends on how fast it is distorted. Ice behaves elastically and may break in a brittle fashion when distorted or strained quickly, but it flows when distorted slowly. Silly putty is a wonderful example of a material that can display the same range of behavior. Stretch it quickly and act like an elastic band. Stretch it rapidly, and it becomes brittle and cracks. But if you pull it slowly or let it settle, it flows as a viscous fluid. Also, like ice, warmer silly putty tends toward viscous behavior, and colder silly putty tends to be more elastic and breakable. On Europa, as the ice crust rides over the changing, elongated shape of the ocean, the cold, brittle elastic surface stretches and compresses and shears elastically, depending on where it is. This distortion results in a corresponding stress within the material. In material science, the word strain means geometrical distortion, while stress represents the internal forces of the material. Stress and strain are two distinct but mutually dependent things. Below the elastic part, a few more kilometers of warmer viscous ice follow along but do not build up elastic stress. To compute the stress field in the surface ice, we model the crust as an elastic sheet overlying the tidally deforming shape below it. For a mental picture of this physics problem, imagine a thin rubber sheath stretched over a slippery spheroid. which changes shape and elongation underneath it. The stress in the rubber will continually change in response to the changing shape of the slippery body that it encases. This model involves various assumptions that are reasonable on a global scale. For example, we assume the ice sheet is continuous and uniform in elastic properties. We must also assume that the ice's elastic properties are similar to those measured in laboratories on Earth. In detail, these approximations are surely inexact, but as a first step toward understanding global stress fields, they are reasonable. Like all physicists, we would rather work with a spherical cow than a real one. Knowing how tides affect the stress on such a crust, we can interpret the tectonic record of observed cracks and ridges. As the Galileo images began to come to Earth in the late 1990s, we realized that the data amounted to a record of tectonic features detailed enough to compare with widely accepted theoretical stress models. I knew exactly how to perform the stress calculations to test the new incoming data against these models. In fact, that is precisely why I was on the Galileo imaging team. In my 1976 proposal, I argued that tides would largely determine what was seen at the Galilean satellites, and I would know how to make the connections. And now, at last, we had the images in hand. However, my options were limited. As previously mentioned, the Galileo imaging team arranged for those responsible for image sequence planning to be the first to report discoveries and publish results. This system ensured that the most politically powerful team members would control the science analysis. My research group at the University of Arizona had been locked out of the sequence planning, so we were also set up to be benchwarmers in the data analysis stage. The imaging team's key geological power players, Ron Greeley from Arizona State University and Jim Head from Brown, divided up the sequence planning and data analysis. Between them, they took control of alternating encounters with Europa, each covering only a portion of the surface with any detail. How they reported, documented, and interpreted discoveries based on separate encounters with the satellite intrigued me. Reconstructing the story of Europa would depend on an integrative approach. Certainly with tides as an underlying force, we needed to address the data by thinking on a global scale, which was my natural tendency as a celestial mechanician. However, both Greeley and Head were geologists who followed the geologist's tradition of working first with particular regions or subsets of the information. That approach is not necessarily bad, but as my student Randy Tufts, an experienced geologist himself, used to tell me, the problem was not that geology is bad. It was that we were seeing it done badly. Whether the science was good or not, the political arrangement locked out my students and meant that Greeley and Head each would control the press reports, the scientific conference presentations, and the initial publications in the scientific literature. Their initial impressions of the images would become the authorized results from the Galileo mission as reported to the world beyond the imaging team. Greeley and Head assigned much of the work on image sequence planning and scientific analysis to their students and postdoctoral associates. Eventually, the Galileo project anointed Robert Pappalardo as a key spokesman regarding Europa. As a former student of Greeley's at ASU and then a postdoctoral associate of Head's at Brown, he was doubly well connected with those in power. My original 1976 proposal to NASA was based on the idea that tides on Europa might be important, and that my interpretation of the images adds value to traditional photogeology. The notion that tidal forces played a critical role had been proven, at least for Io, when Voyager flew past the Jupiter system in 1979. By the mid-1990s, it was evident that interpreting what we saw at Europa would also require understanding tides effects. There would still be an opportunity for my students, associates, and me to figure out what processes might lie behind the appearance of this strange satellite. So my group and I waited impatiently for the initial interpretation by Greeley, Head, and Pappalardo to be completed. We were confident we could bring a lot to the interpretive table. Although I had been appointed to the team for my expertise on tides, they chose not to invite me to collaborate, keeping me locked out of the initial science interpretation. Instead, Pappalardo asked Paul Helfenstein, who worked with his professor Marc Parmentier, on tidal stress calculations in the mid-1980s as a student at Brown University. In addition to being smart, Paul is one of the nicest people in planetary science. He agreed to give Pappalardo the software he had developed to calculate the tidal stress due to non-synchronous rotation. Eventually, my group joined the fray. It turned out, ironically, that the software Helfenstein gave Pappalardo was in an obsolete medium, a magnetic tape format for which no reader still existed. My students, Greg Hopper and Randy Tufts, were monitoring the situation, partly because they were also irritated about being excluded. And I had shown them how to do the stress calculations from scratch. Finally, once Pappalardo was convinced that no usable tape reader existed, he allowed my group to proceed with the analysis. Greg got to work and returned to me within a few weeks with a complete set of calculations of tidal stress. That analysis eventually became the basis for explaining most of the major tectonic patterns on Europa. Figure 5.1 shows a typical stress map graphically representing Greg Hopper's 1997 calculations. It uses a Mercator projection, the same type usually used to make flat world maps of the Earth, with locations given by latitude, up and down on the map, and longitude, right and left. Convention determines the location of longitude 0, just as it does on Earth. On Earth, it is the site of the Royal Observatory in Greenwich, England. On Europa, it is the center of the Jupiter-facing hemisphere. For orientation, the locations of a few of the major global lines are indicated, including Udaeus Linnea and Minos Linnea, cf. Figured 2.4, or Color Plate 2, as well as Astypalia and Agenor, which will also be major players later in our story. The short lines represent the strength and direction of the stress, tension or compression at any point on the surface. The stress pattern here is just an example of these plots. In this case, it shows the stress that would be expected, about 1/8 of an orbital period after the perigove point in the orbit, with a little extra rotation of Europa. The point is that as Europa moves, its body changes shape. Years later, even seeing our publications, Pappalardo was still trying to figure out how to calculate tidal stress. To my surprise, he sometimes presents Greg's results as his own. He can get away with a lot. Such is the power of the mantle of authority, once bestowed by the Galileo project. Like most planetary bodies, Europa probably formed with a spin that was not synchronous, perhaps not even close to synchronous, with its orbit around Jupiter. Every orbital trip around the massive planet likely resulted in the newly forming moon spinning on its axis or rotating multiple times. The rate of Europa's rotation early in its life was influenced by impacts from smaller bodies in orbit around Jupiter that collided with and became part of Europa. The tidal torque would then have slowed the spin to nearly synchronous, at a 1-to-1 ratio, with its orbit. This process would have taken approximately 100,000 years, a relatively short time compared to the solar system's 4.6 billion year age. The rotation would have become precisely synchronous if Europa's orbit were perfectly circular. But it is not perfectly circular, and in the mid-1980s I pointed out that, with an eccentric orbit, tides may cause the spin to settle at a rate slightly faster than synchronous. And Europa is so warm that it cannot support a concentration of extra-dense rock, like the one inside our moon's earthward sector, that helped maintain synchronous rotation. So combining a warm interior and an eccentric orbit makes non-synchronous rotation plausible. Both are effects of the Laplace resonance. First, the resonance drives the orbital eccentricity. Second, the tidal friction results in the internal heating. Still, we don't know whether the rotation is non-synchronous. Theory alone cannot tell us because the strength of the tidal torque is so uncertain. Direct observations, whether by telescope or spacecraft, are limited by inadequate resolution and insufficient observation time to detect changes. However, as we will see in later chapters, much of the tectonic record on Europa's surface could be accounted for by non-synchronous rotation. Over the long term, tens of millions of years or more, Europa's tidal deformation contributes to changes in the resonant orbits of the Galilean satellites, modifying orbital eccentricities and changing the strength of the diurnal tides. In resonance, the periods of the orbits have their 1:2:4 ratio, and the satellites always align in pairs at specific points in their orbits. The tiny gravitational pull that each satellite exerts on the others keeps this configuration stable, as demonstrated by Laplace. Ordinarily, a satellite's effects on the others would be minimal. However, because the geometry is repetitious and periodic, the effects are cumulative and strong, hence the term resonance. Consider what it means to have a pair of orbital periods in an exact ratio of 1:2. Currently, the faster moon passes the other on the inner orbit. We say they are in a conjunction. After that point, the slower one falls behind. The conjunction occurs again only after the faster satellite completes its second lap, which happens to be exactly at the point at which the slowpoke is completing its first orbit. This second conjunction, and every conjunction thereafter, occurs at exactly the same place as the first conjunction did. Remember, Io is in a 1:2 resonance with Europa, and Europa is in a 1:2 resonance with Ganymede. As the middle child, Europa plays a key role in this ballet. Europa's orbit is eccentric. Figure 4.2, bringing it closest to Jupiter at one end of its orbit, known as Europa's periove, and farthest from Jupiter at the other end, its apogee. In the Laplace resonance, the conjunction of Europa with Io always occurs in line with Europa's apogee, and Europa with Ganymede always occurs in line with Europa's periove. In other words, the two conjunctions always occur at opposite ends of Europa's elongated orbit. Fig 5.2. The mutual gravitational effects among the satellites maintain this repeating geometry by adjusting the value of Europa's orbital eccentricity. The closer the periods are to the exact resonance ratio, the bigger Europa's eccentricity must be to maintain the repeating geometry of the conjunctions. This behavior is so weird and seemingly magical that when I first heard about it in 1968, I knew that celestial mechanics was what I wanted to do. Various orbital resonances generally play roles in many of the most important interactions among planetary bodies, because they can enhance mutual gravitational effects. Here I consider only the effects of the Laplace resonance that are most important to Europa's evolution, and I avoid the math that we usually use to describe these amazing interactions. One effect is that Europa's eccentric orbit, forced by the resonance, drives the diurnal tides. Also, tides on Jupiter and the other satellites, as well as on Europa, can actually change the orbital motion of the satellites with major implications for the history of the resonance. Chuck Yoder, a student of Stan Peel's at the University of California in Santa Barbara, developed a mathematical theory in 1979 that showed how the system could have evolved from a non-resonant state into the current Laplace resonance. Europa's orbital eccentricity would have gradually increased to its current value in that scenario. The implication was that tidal effects on Europa would have been much weaker in the past than they are now. Yoder's scenario was widely accepted. First, from a mathematical perspective, it was an incredibly elegant model, and thus appealed to the handful of celestial mechanicians, including me, who understood it. But a seemingly fundamental problem always bothered me. Yoder's analysis depended on a balance between the effects of tides raised on Jupiter by Io and tides raised on Io by Jupiter. He also assumed that Europa tides were negligible in comparison, which may or may not be true. That balance translates into a particular ratio between the heat generated by tidal friction within Io and Jupiter. Now, we know from observing Io's volcanoes just how rapidly heat is being produced there, so the model requires a balancing tidal heating rate within Jupiter. The problem is that no one has figured out how there could be that much friction inside Jupiter. Therefore, 1982, I argued that the system's history may not have involved the Yoda equilibrium. More likely, the tides on Io dominate over the tides on Jupiter. In that case, the system must be evolving away from the resonant condition, in which case Europa's eccentricity would gradually decrease from previously larger values, exactly the opposite of the evolution in Yoda's model. Given that likelihood, I suggested several scenarios that would have led to the system moving out of resonance. One idea was that the satellites had a primordial origin, entering resonance during their formation process. Stan Peele and others did not like the idea. They found it difficult to abandon Yoda's theoretical model, as there was no compelling reason to believe that the process of satellite formation would establish resonance. A convincing mechanism had not yet been demonstrated. Recently, however, new ideas about forming the Galilean satellites have included just such a process. An issue with earlier satellite formation models motivated the revisions. The key issue involves the structure of Callisto, whose density profile, inferred from its effects on the Galileo spacecraft's trajectory, shows that it is only partially differentiated. It was not heated sufficiently to allow the iron, rock, and water to separate by density into distinct layers like those within Europa. How could Callisto be like that? Even if the Circumjovian Nebula had barely enough material to build the Galilean satellites, accretion would have been so fast, and the temperatures would have been so high that Callisto should have become fully differentiated. Robin Canup and Bill Ward of the Southwest Research Institute in Boulder have addressed this problem by proposing that the satellites were formed later, near the end of Jupiter's formation period, while dust and gas were flowing from the solar nebula into Jupiter through an accretion disk around the giant planet. They calculated that the satellites could form slowly within the accretion disk, consistent with the amount of internal differentiation now found in each satellite. Most importantly, for the history of orbital resonance, the gravitational interaction of the growing satellites with the accretion disk caused their orbits to migrate. They would induce spiral waves in the accretion disk, similar to the spiral waves in galaxies or Saturn's rings, and their gravitational interaction with the waves would change the satellites' orbits. This migration of orbits provided a way for the Laplace resonance to get started as part of the same events that formed the satellites, as demonstrated in 2002 by Stan Peele and his postdoctoral associate Man Hoi Lee. After the formation in resonance, tides on the satellites would modify the orbits, decreasing the orbital eccentricities from higher early values, as I had described in my 1982 paper. It was personally gratifying that my conjecture was proving plausible. Even better was that Peele and Lee acknowledged that I had it right. The scenarios I proposed in the early 1980s differed from Yoda's equilibrium model, in that Europa's orbit would become more circular, not eccentric. Given the tidal friction apparent in Io from all that volcanism, significant change in orbits might have occurred within the past 100 million years. That timescale is strikingly similar to the probable 50 million year age of Europa's surface. When the oldest features currently visible on Europa formed, the satellite's orbital eccentricity would have been substantially larger. All the tidal effects, heat, stress, etc., that are so important on Europa now would likely have been even stronger in the past. A natural question is whether there is evidence for change in the geological record over the past 50 million years as the eccentricity decreased. In fact, the canonical Galileo reports on Europa's geology claim to have found such evidence. Alleged changes over time, particularly in tectonic features, were shown as signs that the icy crust was getting thicker, which was thought to match less tidal heating. Moreover, the party line declared chaotic terrain as the youngest type of surface on Europa, which formed only late in the 50 million year age of the surface. The canonical storyline was that chaotic terrain formed from convection in the solid ice, and that the ice only recently became thick enough for convection and subsequent chaos formation. So, The emerging geological party line implied a gradual decrease in tidal heating over the 50-million-year age of the current surface. That story fits perfectly with my old theory that Europa's eccentricity had decreased for about that time. I should have loved that story. It was wonderful in so many ways. For example, it showed how different pieces of evidence from planetary science are connected, like figuring out the age of Europa's surface by looking at the few craters and comparing them to how often comets and other small objects hit it, along with the theory about its orbit that relies on the heat coming from Io. The geology confirmed the predictions of theoretical celestial mechanics. As the leading advocate for such orbital evolution and having taken considerable flack for it until Peel and Lee came around, I should have found it gratifying. And the geologists were eager to cite and credit my predictions. I could have been a hero if I had kept my mouth shut. The problem was, I found the geological arguments unconvincing. The geological time sequences were based on ad hoc interpretations of the images. Geological mapping exercises purported to show changes in tectonic style or thermal processing were ambiguous and subjective. The argument based on chaotic terrain made the least sense to me. As my students and I studied the images, we saw no evidence that chaotic terrain was especially recent. To be sure, Connemara chaos was a very fresh feature, but it was selected as a target for detailed imaging precisely because it was so fresh and obvious. Yet even there, we could see the cracks and ridges that were already beginning to cross it. Figure 2.9. As we surveyed the surface, we could see that over much of the surface, hidden under densely packed strands of newer ridges, lay ancient areas of chaos. The putative freshness of most chaotic terrain was an observational artifact. It is simply easiest to spot the examples of chaotic terrain that formed most recently. Moreover, even if chaotic terrain formation was only a recent process, the argument that implied ice thickening over time seemed completely backward. The appearance of chaotic terrain argued for ocean melt-through exposure, with rafts drifting to new positions. That interpretation would suggest that the ice had gotten thinner with time, not thicker. In fact, even before I had gotten into the fray, there was a battle among the imaging team geologists over this point. The wonderful pictures of Connemara chaos were a major early accomplishment. The veteran planetary geologist Mike Carr of the U.S. Geological Survey was the team member assigned to lead the preparation of a paper for the influential and prestigious journal Nature, reporting on this discovery. Like most people who looked at those images, Carr interpreted Connemara as a site of a relatively recent melt-through of the ice, exposing the ocean below. For a brief period in early 1977, that was the official story for the media. For example, in April 1977, Carr and project scientist Torrance Johnson described Connemara in those terms during an interview on the PBS McNeil-Lehrer news show. And that is how Connemara was described in Carr's early drafts of the Nature paper. However, in the same time frame, Bob Pappalardo and his mentor, Jim Head, had begun to promote their view that everything on Europa involved thick ice and solid-state processes. The keystone of their case was the putative existence of a class of features they called pits, spots, and domes. Although that taxonomy has since proven premature and its generalizations incorrect, see Chapter 14. Pappalardo received support from his mentors and took the lead in preparing an imaging team paper that supported solid-state convection in thick ice. The plan was for Pappalardo's paper to appear as part of a set of papers in Nature that would present the early discoveries of the Galileo mission. The problem was that his supposed evidence for thick ice directly contradicted Carr's interpretation of Connemara, which was to be published in the same issue of Nature. Having become the spokesperson for the imaging team regarding Europa, Pappalardo had a platform of authority to promote his views. A lot of pressure was applied while preparing the Carr et al. Paper, So even though some parts show the idea of ocean exposure, the paper ultimately supports a somewhat unclear solid-state formation process for chaotic terrain. From that time forward, thick ice became the obligatory canonical model. Pappalardo expressed surprise that I did not jump on the thick ice bandwagon. It would have been excellent for my career. The new canonical story's chaotic terrain was a sign of the recent thickening of the ice. It fits perfectly with my early calculation that tidal heating must have decreased with time. This would have established my role as the team's celestial mechanics guru. Regrettably, I could not accept the purported geological proof that the ice was so dense that it separated the ocean from the surface. Not only did I reject my appointed role in the official Galileo narrative, but I was also infringing upon the rights of the geologists. My life would have been so much easier if I had gone with the canonical flow, but being me, I had to follow the evidence where it took me. The fact that there is no clear evidence of change in geological processes over the recorded geological history does not mean the orbits did not evolve. More recent resurfacing may have destroyed the evidence for such change, or it might be too subtle to recognize. Equally plausible is that the geological processes recorded on the surface have been continuous throughout the surface's history and continue currently. Instead of other evidence, Occam's razor favors that simple interpretation. Studies of orbital dynamics are continuing. We need to understand how tides raised on Europa and Ganymede may have affected the evolution, especially if we consider the accompanying changes in the geophysical states of the satellites, and how they feed back into the orbital evolution. Historical measurements of orbital periods might help. We have a useful record of observations that goes back to Galileo's original 17th century data on timing the orbits, and Kara Aksnes, University of Oslo, and Fred Franklin, Harvard-Smithsonian Center for Astrophysics, have been investigating the evidence for changing orbits. These orbital studies and detailed investigations of what is seen on Europa may play key roles in clarifying the geological and geophysical history. We can also make predictions for the future. Europa has had an ocean and an active surface recently, probably continue global cracking patterns. Paul Helfenstein and Marc Parmentier at Brown University made the first direct connection between Europa's geology and tides in the early 1980s. They showed that the long lines on Europa's surface are mostly at a right angle to where the tidal forces are strongest in the crust, a connection mentioned in the last chapter and visible in the stunning global map created by the US Geological Survey after the Galileo mission. You would expect a crack to form perpendicular to the tidal tension, so this general correlation of lines with stress tells us that these lines represent cracks. Yet most of these linear features do not look like cracks. During our surface tour, we observed that these linear features are typically triple bands, composed of ridges with dark margins upon closer inspection. Moreover, the ridge pair is the common denominator of all the ridges. So, each double ridge marks a hidden crack, probably in the valley between the ridges. The correlation is important to how double ridges and adjacent surface darkening, the triple bands, develop. Looking more carefully at the crack patterns, we can use them to record Europa's past. 1986. Alfred McEwen mapped many of Europa's surface lines using Voyager images. McEwen was then a graduate student at Arizona State University and worked at the US Geological Survey's Astrogeology Center in Flagstaff, Arizona. He became a member of the Galileo imaging team. He is currently my colleague on the Planetary Sciences faculty at the University of Arizona, where he directs the Planetary Image Research Laboratory, whose students and staff have produced some of the most spectacular and revealing versions of Galileo images. McEwen found evidence supporting my idea that Europa might rotate non-synchronously. He noted that many cracks are about 25 degrees too far east relative to the expected stress patterns. For example, if we moved Minos Linnea 25 degrees further west. Figure 6.1. It would fit the tension pattern much better. Evidently, after tidal stress caused the cracking, further rotation of Europa carried the cracks eastward, relative to the direction of Jupiter, to their current positions. While some minor details in McEwen's paper could be debated, the main principle remains crucial. We can decipher the crack record to determine the relative age of individual features based on how far west they must have formed. Generally, we could use the crack patterns to explore the satellite's history. And the patterns from the Voyager images seem to support my idea that Europa might be spinning non-synchronously. A decade later, the arrival of early Galileo images primed us to search for further evidence of Europa's rotational history. The first clear signs of a pattern of cracks that might be connected to non-synchronous rotation came from Paul Geisler's skill in using multispectral remote sensing and his talent for connecting intriguing findings with basic theories. To consider the images that Paul used, it may be helpful to understand how the Galileo spacecraft got them. During each of its orbits around Jupiter, the spacecraft generally spent a good fraction of its time very far out, and then it swooped into the neighborhood of the satellite's orbits. Generally, the satellite's positions were far apart, so the Galileo craft did not fly close to more than one satellite during each orbit. The swoops were labeled with the orbit number, starting with the first one after the spacecraft entered orbit around Jupiter, and a letter identifying the satellite encountered in that orbit. Thus, the first orbit was called G1 because it involved a close targeted encounter with Ganymede. E2 was the first encounter with Europa. The letter is redundant, since only one satellite was targeted on each of Galileo's orbits, but the E or G serves as a reminder of which satellite was favored on each swoop. With orbit G1 targeted on Ganymede, Galileo did not get close enough to Europa to get high-resolution images. But it did get a set of images at a resolution of about 1.6 kilometers per pixel, covering a wide region around the Eudaeus-Minos intersection. The same region was imaged several times using the same black and white camera, but each time through a different wavelength filter. Each image recorded the brightness of a certain range of wavelengths of light, many beyond those visible to the human eye. Many were at wavelengths in the infrared, even longer than red. These images provided just the kinds of data Paul Geisler loves. He obsessively combined the data collected through different filters to produce a stunning variety of color composites. Paul, who usually worked at night, was so excited that he spent the entire day perfecting these beautiful images. But while they were pleasingly colorful, they did not show what the human eye would have seen on Europa's surface, which would appear white and bland. Instead, to get at the information that interested him in the image data, Paul exaggerated the color and contrast and made color substitutions as needed. For example, some color pictures represented combined images taken through filters at infrared, red, and green wavelengths, and they were displayed as a combination of red, green, and blue, the standard components of color TV. Color Plate 2 is one of these products. As a result of different versions combining filters in various ways, Paul's images showed Europa's ice in shades of pink and blue, with the dark lines bordering the triple bands in shades of orangey brown. When I first hired Paul to assist with one of Galileo's brief encounters with Earth en route to Jupiter, he applied the same technique to images of Antarctica, captured by the spacecraft, using the same camera later employed for imaging Europa. For Antarctica, he had discovered that in his false color images, the pinks and blues could distinguish between the sizes of the grains of ice in snow and clouds. For Europa, Paul could tell us how the ice grain sizes varied from place to place. And for us, there was an even greater payoff. Enhanced images showed something that excited my whole research group. Paul noticed that he could easily distinguish which lineaments crossed over others. These show up clearly, for example, in color plate 2. So these cross-cutting relations revealed the order in which the linear features were created. Invoking Occam's razor, we assumed that older lines mean older cracks. Then Paul noticed some patterns. The older the dark-colored markings, the more they appeared faded. With increasing age, the dark margins of the triple bands seemed to revert to the coloration of the surrounding terrain, e.g. Sir. Color plate 2. Paul found that the oldest lineaments are fairly bright and white. The intermediate age ones are the triple bands with their dark margins. The youngest were faint, thin lines, which we interpreted as cracks that had not yet had time to develop ridges or dark margins. The most striking pattern was an orderly sequence of orientations that changed systematically with age. The most recent lineaments trend roughly northwest to southeast. Older ones run more nearly east-west, and the oldest runs southwest to northeast. The orientations will systematically rotate clockwise in the future. Moreover, the trend was followed even among the intermediate-aged triple bands. We can see that Eudaeus crosses over Minos at the intersection of the triple bands near the region's center, following the general trend where the younger feature is oriented further clockwise than the older one. The changing orientation of lineaments inferred from Galileo's first orbit, G1, suggested a systematic clockwise rotation of the direction of tension in the Eudaeus-Minos region over time. At one of our weekly research group meetings, where my students and postdoctoral associates discussed their progress and plans, Paul insisted that we compare this clockwise trend with the tidal stress plots that Greg Hopper had been computing. It was an excellent idea. So we sketched the positions of Eudaeus and Minos on a stress plot, similar to the one shown in Fig. 5.1 and the inset in Figure 6.1. A remarkable pattern jumped out from this comparison. A clear pattern emerged from this comparison. If the real estate in the G1 images had shifted from the west to the east over the last few degrees of longitude to where it is now, it would have passed through an area on the stress diagram where the local tidal tension would have turned clockwise, similar to the changes in the lineament directions that Paul observed. The tension would have changed in a direction perpendicular to the lineaments Paul had mapped, but to a similar extent. This discovery provided additional compelling evidence for non-synchronous rotation. In the past, the Eudaeus-Minos region had been further west, where tidal stress caused the older cracks to form. Later, as Europa rotated non-synchronously, this region and the entire surface moved eastward. That is, it moved eastward relative to the direction of Jupiter, and by definition, it moved eastward relative to the longitude system. Jupiter generated the stress field, and as the real estate around Eudaeus and Minos moved eastward, it underwent ever-changing tidal stress. So the more recent cracks have a different orientation from the older ones. This discovery made for a very exciting debate in my lab. Paul and my students, Greg Hopper and Randy Tufts, overcame every objection I could raise and convinced me that we had evidence for non-synchronous rotation. The result was quickly accepted within the Galileo imaging team and then more widely after we described it in a couple of papers for which Paul was the lead author. It was compelling because the data showed several sets of lineaments that were progressively and continuously more clockwise, with decreasing age over a few tens of degrees of rotation. The appeal of the interpretation lies in its elegant linkage of several lines of quantitative research. It confirmed my own much earlier predictions, based on tidal theory, that Europa might be rotating non-synchronously. It clearly corresponded with the beautiful images Paul produced using state-of-the-art image processing and quantitative multispectral analysis. And it resulted in the discovery of unexpected systematic trends that fit Greg's computed tidal stress field. I had several reservations about this model. One of them later turned out to be important. Once a crack had formed in the Udias Minos region or elsewhere, it would have relieved the stress. You would not expect more cracking in the neighborhood until either the first crack froze shut or the direction of the tension changed a tremendous deal. Both of those things would take a long time. Once a crack forms, diurnal tides must continuously work it. As described, the cracks must remain open and active for a long time to build the ubiquitous ridges. It would take a long time before a crack would freeze shut and allow tension to build up again. So, even as I supported Paul's story, I worried about how so many cracks could have formed with orientations that changed only gradually from one to the next. The lines visible in those early low-resolution images from G1 must be among the youngest on the surface. Paul's study of changes in color over time showed that older features blend back into the background. Given that Europa's surface is less than about 50 million years old, and that the lines involved in Paul's rotation analysis are much younger, Europa's non-synchronous rotation period, the period relative to the direction of Jupiter, would seem to be less than a few million years. A Jupiter-facing hemisphere would shift away to a different direction in less than a million years or so. That constraint on our estimate of rotation speed is not very tight. It could be much faster, but not much slower. What other constraints exist on how we estimate the rotation speed? It must be slow enough for ridges to grow along each crack. Otherwise, if the rotation were too fast, the crack would quickly move east to a place where the stress is different from where it formed, and so it would freeze shut before it could grow ridges. Based on estimates of how quickly ridges grow, the rotation period cannot be less than 100,000 years. So far, we have constrained the rotation period to less than a few million years and more than 100,000 years, long enough for ridges to grow. Could we be more precise than that? From the beginning of the Galileo project, I aimed to measure the satellite's rotation by direct observation. Taking pictures of a satellite at two different times should, in theory, allow us to determine whether it rotates. In practice, there are problems. In a photo taken from a moving spacecraft, the exact position of a reference feature on the surface may be difficult to define. Shortly after Greg Hopper asked to work with me as a PhD student, I suggested we try to solve this problem. The best strategy was to compare Voyager and Galileo images, because they would give us the greatest interval between observations and the best chance to see motion. We also decided to use Europa's terminator, the visible boundary between the dark night and bright day sides, as a position reference. Its direction in space was well defined by the precisely known position of Europa relative to the Sun. With Paul Geisler's help, Greg found moderate resolution images of a particular region taken by both spacecraft 18 years apart, each of which showed the position of the terminator at the time the picture was taken, Fig 6.2. We knew the terminator position at the time of the Voyager image and the exact time interval between the two images. We could predict where the terminator should have been on the Galileo image if it had been rotating synchronously. Greg faced some technical challenges during the analysis but concluded that the terminator was precisely as predicted upon completion. The evidence was consistent with synchronous rotation. Greg and I were dejected. We'd hoped to detect something more interesting. Paul Geisler noted that the uncertainty in Greg's measurements would not have resulted in the loss of anything. No measurement is exact. In fact, the terminator is fairly wiggly due to the effect of topography. Ridges and bumps cast shadows that distort the day-night boundary. Greg calculated the uncertainty in the measured rotation to be about 0.5 degrees. In other words, Europa might have rotated as much as an extra half degree in 17 years, relative to synchronous rotation, equivalent to one full rotation in about 12,000 years. We now had a period of rotation within the range of 12,000 to a few million years, while the existence of ridges probably required a period longer than about 100,000 years. At the end of the 20th century, with Galileo still orbiting Jupiter, things were not precise or certain. The orientations of the cracks in the early G1 images are perfect evidence to compare with theoretical calculations of stress and thus infer rotation. Paul Geisler's discovery of a systematic change in those orientations in the Iudaeus Minos made for a compelling story. But a few years later, we found an even better way to pinpoint where particular cracks had formed. Voyager images of Europa have revealed a peculiar pattern of ridges, figure 6.3. As viewed from above, they form chains of arcs called cycloids, so designated because of their similarity to the geometric shape of that name. The official nomenclature of the International Astronomical Union calls them flexible, but it's the same thing. One of these cycloids was never named by the IAU. When my student Mike Nolan did a survey in the early 1990s of cycloid properties from the Voyager images, he labeled this one G in honor of his thesis advisor. Later, when Hopper et al. Published the paper showing how these cycloids constrained Europa's rotation period, that notation was retained. And to my students' amusement, I became the only person to have had a feature on Europa named after himself. The changing stress of diurnal tides directly contributes to these distinctive crack patterns. With that knowledge, we can pinpoint where any cycloid must have formed relative to Jupiter. 2000 Greg Hopper showed how this information could constrain the rotation period. He thought about the cycloids found by Voyager, which seem new since they cross most of the area's features. Since Paul learned about regular changes in the Iudaeus Minos region, we thought the cycloids would have formed similarly, following a neat west-to-east pattern over a small number of degrees of rotation. Greg's results did support the idea of non-synchronous rotation. To fit the theory, the shapes of cycloids required that each one must have formed at a specific place farther to the west. Those places ranged over several tens of degrees of longitude. Although they all formed in the same area on the ice, each cycloid formed at a different time while the ice moved eastward to its current position. If that were true, the order in which these cycloids formed, as inferred from how the ridges crossed over one another, should match the west-to-east order of their formation longitudes. A younger cycloid should be closer to its current longitude than an older one, and if it crosses, its ridges should cross over the older one. Instead, Greg discovered that the orders had become jumbled. The age sequence inferred from the ridge crossings did not match the order inferred from the location where they formed. We resolved this conundrum by noting that a cycloid that moved eastward to its present location might have undergone additional non-synchronous rotation cycles. For example, a feature that formed a few degrees west may have rotated an extra 360 degrees before it reached its current longitude. Tidal stress is symmetrical, so the inferred formation location of any cycloid could be another 180 degrees farther west, which also helps us sort out the age sequences. So Greg was able, by invoking extra rotation periods, to reconcile the age sequence based on ridge crossings with the ages based on where they formed. That result implied that no more than a couple of cracks form in a given region during a non-synchronous rotation period. That rate is reasonable if each crack relieves the tidal stress in its region. Tidal stress cannot begin to accumulate again within that region until the crack anneals. That result was reasonable, but its implication was disturbing. It was inconsistent with the inferred history of the Iudaeus Minos region, where many cracks seem to have formed in only a small fraction of a rotation. Ignoring the problem for a few years, we examined the consequences of only a few cracks forming in a specific region during each rotation period. The region around Sidon and Delphi Flexi is roughly 800 by 1,000 kilometers, as shown in Fig. 6.3. Presumably, it has completely resurfaced in the past 50 million years, just like the rest of Europe. If a typical crack like Sidon or Delphi yields a ridge pair about 2 kilometers wide and 1,000 kilometers long, a minimum of 400 cracks would be needed to resurface the area. That would take at least 200 rotations if only a few cracks form on each turn. Having 200 rotations in 50 million years means the period must be less than 250,000 years. This result allows tens of thousands of years for each new crack to remain actively worked by diurnal tides before it moves away, freezes shut, and lets stress build up again to create the next crack. That amount of time is sufficient for the ridges to grow through the process described. Most significantly, this line of evidence reduces the upper limit of the non-synchronous rotation period from millions of years to only 250,000 years. We use the lower limit of 12,000 years derived from comparing Voyager and Galileo terminators to estimate an approximate rotation period of 50,000 years, allowing for a factor of 5. That analysis was based on only one region, Europa. Given how widely distributed cycloids are on Europa and how many we have imaged, the work on the cycloids in the Astypalaea region should be considered only a pilot study. It demonstrates, as a proof of concept, the potential for future studies of the tectonic record to help unravel the history of Europa. Europa's dynamic history will be laid out and ready to read when future spacecraft obtain more complete global coverage at adequate resolution and with appropriate illumination. In the meantime, the data from the Galileo mission has not yet been fully exploited, and it probably still has a great deal to reveal while we wait to return to the Jupiter system. The problem remained that if only a few cracks could form during each rotation of Europa relative to the direction of Jupiter, which seemed reasonable, how could we explain our earlier contradictory results from the G1 images of the Eudaeus-Minos region? That earlier work was convincing and universally accepted due to its compelling evidence and logical reasoning. The model elegantly explained several lineaments that progressively and nearly continuously rotated clockwise with decreasing age. The original method was so attractive that many other researchers started to arrange the geological record according to a supposed order of slow, steady changes in the directions of cracks. Geological mapping of various regions used linear feature orientations to put their ages in order. Geological timelines patterned on the formats of terrestrial stratigraphy incorporated this information. Geologists use the word stratigraphy to mean a time sequence of events because on Earth, widespread layers, or strata, have built up over time, and their study has been a key to understanding geological history. There is no evidence that stratigraphy is a meaningful concept on Europa. Various geological studies took observed linear features and structured them into systematic scenarios modeled on Paul's study of the Eudaeus-Minos region. Many people, including some of the powerful players on the Galileo imaging team, became deeply invested in the idea of the generalized phenomenon we'd proposed: a smooth, systematic variation of crack orientations. The problem was that we received support when we no longer were sure we wanted it. Models in which numerous cracks formed during a fraction of the rotation period were precisely contrary to what we had inferred from the cycloids in the Voyager images. This inconsistency with Paul's early model was not widely appreciated, but Greg Hopper kept reminding me about it, pressing the case for an inconvenient truth. Because my group was responsible for the evidence on both sides, the azimuthal variation in the Eudaeus-Minos region and the cycloids in the Voyager images, it seemed especially important for us to resolve the contradiction. So, we decided to return to the Eudaeus-Minos region, where the low-resolution images from orbit G1, color plate 2, had provided compelling and widely accepted evidence for non-synchronous rotation. The earlier work was solid for its time, but it was based on the limited data from the first orbit, G1, when Galileo had not even come close to Europa. Strangely, even though this same region had been imaged at a much higher resolution, 200 meters per pixel, during orbit E15 back in the 20th century, as late as the summer of 2002, no one had used these superior images to check what we had done with the G1 data. Examine the difference in detail between Figure 6.4 and Color Plate 2 when comparing the E15 images. Late that summer, Alyssa Sarid began her senior year at the University of Arizona. She had already done a major study of the E15 images during her junior year. Because she was already an expert on tectonic features in the E15 images, I asked her to help me use them to check our results from the cruder G1 data. The first step was a survey of all intersections of ridges or other linear tectonic features in the same Eudaeus Minos region we had studied in the G1 images. In an ideal dataset, every crack in the selected area would cross the next oldest and youngest, and the appearance of the intersection would unambiguously display their order of formation. Assuming that the expected rotation of the tidal stress field, clockwise in the northern hemisphere, controlled cracking, the newer crack's orientation, the azimuth, should be further clockwise than the older one. Of course, there is an ambiguity. By analogy, if a weather vane changed from north to northeast, you cannot tell if the wind direction changed by 45 degrees or 315 degrees in the opposite direction. Similarly, if a newer lineament on Europa seems to be oriented further counterclockwise, it may have formed after the stress rotated much further clockwise. Once Alyssa made the measurements and sorted it all out, she found that putting the features into a time sequence required the direction of crack formation to have spun at least 3 times over the time these cracks formed. The pattern of crack directions we figured out a few years ago from the low-resolution G1 data covered just a small range of angles, only a tiny part of one non-synchronous rotation period. Upon close inspection, the new results contradict the earlier interpretation. We looked at the features in the G1 study and checked how they matched up with the larger sequence from the E15 images. We found several new lineaments that fit between the G1 lineaments in the formation sequence. Even though the lineaments identified by Paul seem to lie within a fairly narrow range of orientations, the new results indicated that they did not all form during a single cycle of non-synchronous rotation. Evidently, the selection of identifiable lineaments in the G1 images represented a smooth, continuous change in azimuth over a few tens of degrees, merely by chance. We concluded that the cross-cutting record described does not support non-synchronous rotation. Alyssa investigated several other regions of Europa using the E15 images, and others from later orbits, all with the same result. Although there is a rich record of cross-cutting relationships, there is no compelling evidence in that record for non-synchronous rotation. That result does not mean Europa rotates synchronously, only that there is no smooth uniform variation with many cracks formed in a single rotation. It is perfectly consistent with our earlier results based on the cycloids in the Voyager image, which indicated that only a couple of cracks could form in any region per rotation period. In fact, with cracks forming so infrequently, we would expect no record of recognizable azimuthal variation, even if Europa has been rotating non-synchronously. I was surprised by the aggressive attacks Alyssa faced when she presented these results at several scientific conferences. Initially, I anticipated that a young undergraduate would have received at least some consideration. She also brought the news that the previous interpretations made by my group were now being questioned. We were comfortable with that result, so it is understandable if others feel the same way. The issue arose when Galileo's canonical set accepted our earlier interpretation. They took ownership of the idea by using it as the basis for their geological interpretations. Now, by reversing our earlier result, we were betraying their trust. My approach to science has followed the evidence where it takes us. Good science, but bad politics. Ironically, in this case, our discovery challenged the established canon. While our 1998 interpretation of the G1 data was reasonable given its limitations, the better images from orbit E15 showed us that the case for non-synchronous rotation from lineament azimuths is hardly compelling. Similarly, continuing investigations of the large data acquired over the entire Galileo mission can provide a more profound understanding and correct misconceptions based on the earlier limited data. It seems likely that Europa does rotate non-synchronously, but not based on the evidence we perceived at first. Images already in hand will provide greater insight into many of the issues regarding Europa. We need to exploit all that information and follow its implications. If we change our minds about what Europa is like, it will not be a sign of failure, but of success in pushing forward. We still need to explore and fully interpret the images and other data from the Galileo mission. We must complete this work to validate the investment in the Galileo mission and set the stage for future spacecraft exploration of Europa. I'm invested in modeling European tectonics regarding the effects of tides and non-synchronous rotation. But I'm open to the idea that we may be wrong, or that things are more complex than we think. In various areas, there are favored orientations for cracking. Perhaps some pre-existing weakness in the ice is a dominant effect, obscuring any evidence of rotational movement. Alternatively, the entire global crust may occasionally shift relative to the spin axis. We shall see evidence developed by Alyssa that such a polar wander did occur. Such slipping of the whole crust around the planet could have happened repeatedly, either at random or in some systematic way that we do not yet understand. In that case, a dominant driver of tectonic cracking is the crust stretching that occurs as it reconforms to the tidally elongated figure of Europa. From the point of view of computing tidal stress, polar wander is a non-synchronous rotation in arbitrary or at least unsystematic directions. If it happens suddenly, tremendous stress would ensue, possibly dominating the tectonic record. We have only begun to consider the range of possibilities. The tectonic record holds the story, ready for us to read. In the following documentary series, we will consider how cracks manifest themselves in the visible record of Europa's surface evolution. The most common sign of an underlying crack is the ubiquitous double ridge